Asia to deal with the multi-hazards early warning system and what possible way forward for the next few years. So if you just look at various types of weather phenomena which occur throughout the globe and which is also feasible in Southeastern region, you will find that there could be very small scale systems like DOS and decadal scale or scale of years together. There are also changes in the atmospheric circulation patterns and atmospheric behavior in terms of its impact with respect to the extreme weather. So considering all these from the very early ages, people tried to improve the monitoring, forecasting, and early warning for various types of natural hazards, especially the weather-related hazards. The weather-related hazards are almost 80% of the total number of natural hazards which affect the globe, and especially the South Asia also. So considering that when we came up with the instrumentation age, say in 1850 or so, with the industrialization, people also tried to have various types of instruments for monitoring closely the atmospheric phenomena and oceanic phenomena also. And gradually the improvement came, and at present we are in a position globally and also in South Asia to detect any large-scale synoptic scale weather events which can cause the hazards and disasters. At the same time, there are certain small-scale events still now, say for example, the cloudbursts, flash floods, which are still challenging and need some further action to improve its management. So if you just look at the hydrometeorological hazards, which I am concentrating on in this talk, its management, if you just look at, there are various phases. So during the disaster, certainly you have to take the actions for management of the hazards so that you can minimize loss of lives. And so in the pre-disaster actions, depending upon the proneness of the hazard, vulnerability, and risk, you have to be prepared. The preparedness action is one of the most important action for any society to deal with any types of hazards, and especially the hydrometeorological hazards. At the same time also, we have to prepare and plan for mitigation, prevention, and risk reductions. So as you know, that risk depends upon hazard and vulnerability and exposures. So therefore, we have to plan together all aspects of hazard, vulnerability, exposure for prevention and mitigation so that we can reduce the risk due to disasters. At the same time, during disaster, the response actions are very important. If people do not respond, even if you give the warning, then disaster cannot be mitigated. So you need, therefore, a realistic and very responsive system in place. And there are many examples where people do not respond. In recent years, if I take Cyclone Nargis in 2008, 140,000 people died in Myanmar. The forecast was given by Regional Specialized Meteorology Center, Delhi, and which was appreciated by WMO, but still people died. So it was a very, you can say, a very precarious situation when you are getting appreciated by WMO for giving the warning, but at the same time people are dying. So what does it mean actually? So that means early warning is there, but there is no response to early warning. There are many reasons why there is no response to early warning sometimes. It may be because of the lack of confidence of the people in disaster managers, or it may be because of the lack of consistency in the warning issued by the agency and the accuracy level of the warning. But however, over the years, it has improved, and the response section also has increased by many countries, and including in South Asia, which has resulted in loss of lives being minimized. So after disaster also, there are certain actions for relief, rescue, and recovery. And there also, early warning plays a dominant role for the early warning management scheme and also for the disaster management scheme. Those who are at the vulnerable places, those who are at the cyclone shelters or in the flood shelters. And they need also continuous information so that relief, rescue, and recovery actions can be taken up well. So therefore, if I just look at the components of early warning system, I'll say that it starts with the monitoring of the hazards. So you should have a proper system for monitoring, analysis, and detection of the hazard first. Then you should have the predictions. Now, once you predict the system, if you really want to minimize the risk due to disaster, you should have an impact-based forecast and risk-based warning. Now, once you generate the warning, it should be presented properly so that each and every stakeholder and the media, public, disaster managers can understand it and take response actions. Warning dissemination also follows it. Warning dissemination should take into consideration the latest information and communication technology, and so that it reaches out to the last mile. It is not simply that the message should reach the last mile, but it is also very important that message is readable, message is actionable, message is simple, message triggers the response. So for that purpose, you have to speak the early warning in terms of the language of the stakeholder. Then, of course, even if you issue all these warnings, etc., you have to coordinate with emergency responders, say state government, central government, ports authorities, or any authorities, flood management authorities, or say lightning and other small-scale events. So that coordination is very important. That builds up the confidence among the emergency responders, and maximum update can be provided frequently, and therefore integrated way can be approached for management of this one. Then each and every system has to be reviewed. We should review each and every disaster, how far we have succeeded from the previous one and how far we lagged, what are the lessons learned, and that lessons learned will help further to improve in the next disasters. So to carry out all these things, there should be regular review and regular update by each and every component of the early warning system. So pre-event exercise is also very important. Pre-season exercise is also very important. Every season, if you know that this is the season of floods, for example, monsoon season, so prior to monsoon season, there should be some kind of exercise. Maybe you may be a mock drill, or you may have some other actions as planned, as it is being planned in certain countries also. Similarly, prior to the cyclone seasons. So this helps to fine-tune your current status, and also it helps to build the confidence among the disaster managers. Essential for all these aspects what we discussed so far. But in addition to that, also you need information about the hazard monitoring and assessment. Okay, if really we want to prepare for prevention mitigation aspects for a particular area, then we should know at least what is the hazard potential for that particular area, and which hazards are possible in that particular area, what is the timeliness of that hazards, and how intense are those hazards for a particular area. So that hazard analysis and accordingly vulnerability analysis and exposure and risk analysis should be carried out based on the past historical data. And there also you have got in role of the early warning system agencies. And of course, we have got the technical support for vulnerability analysis and risk assessment, preparedness and planning. No preparedness and planning can be carried out by the disaster managers without the input from the early warning agencies. So early warning agencies also to provide all the relevant technical materials for the purpose of preparedness, planning, prevention, and mitigations. There are certain natural resources, like say water bodies, and you have got say agriculture, you have got energy sources, which are most affected by the disasters. So therefore, specific actions are required for those management, and there also the technical support from early warning agencies is very important. So if we just have a generalized view of what an early warning system is, this slide explains that it starts with the observations. You should be able to detect the particular hazard. For this purpose, globally, all types of observations are utilized, especially when you consider South Asia. It is a very data-sparse region. In the South Asia, you have got the Great Himalayas in the north, and you have got the Bay of Bengal, Arabian Sea in the east and west, and Indian Ocean to the south. Also, you have got many hills like Myanmar Hills and Western Ghats, Eastern Ghats, and many other. Also, you have got the deserts in the west covering Pakistan and some parts of northwest India. So therefore, there is a varied physiography and the data sparse region. So therefore, what we do actually, like just like globally, we go through all types of available data, just like beggars are not choosers. So you have to consider all types of data, whatever available. And remote sensing data, especially from satellites and radars, play a dominant role to assess the current status of the ocean, atmosphere, and Earth system. And these data, which are collected with a network of observations, both direct and remotely sensed, are fed into a forecaster's decision support system. There, a forecaster analyzes and find out the current status, evolution, characteristics of various weather systems. And at the same time, all these data are digitized and fed into a computing system. And that computing system nowadays people say HPCS, that is high performance computing system, which has got a capacity of about 10 petaflop in India. And in other countries also it may be higher in certain countries like USA, UK, and Japan. So with that high performance computing system, an array of mathematical models are solved to simulate the current atmosphere and hence to predict the atmospheric phenomena or oceanic phenomena for different space and time scales. So accordingly, there are different types of models: global models, regional models, ensemble models. Ensemble models are those models which take care of the models of models. You can say a set of combination of models. There are two types of ensembles: multimodal ensembles and single model ensemble systems. And these ensemble models helps you not only to predict a particular weather hazard, but also provide you the probability of occurrence, probability of intensity, etc., of that particular hazard. Now, once all these numerical models are run, you have the guidance from these models. So the forecaster is now equipped with two types of information. So one is the current information based on the observations. Other one is the information derived from an array of numerical weather prediction models. So he utilizes or she utilizes a decision support system where he can compare, comprehend, and analyze various types of weather systems, various types of observations, and various types of model forecast, and takes a decision. So to help that, there are many statistical tools or statistical forecast to take a decision. At the same time, the numerical modeling system has not come up to that way so that you can use it directly. And still there is scope to improve the numerical weather prediction system for predicting the various types of weather systems. So therefore, the subjective analysis based on the experience, expertise, and knowledge base of the forecasters still play a role, just like a medicine specialist. So a medicine specialist, whatever may be the diagnosis based on instrumental detection of a disease, so finally, the medicine specialist takes a call based on his experience, knowledge, and expertise. He may reject some of the observations derived from X-rays or derived from ultrasounds, and he may take its own decision. So that decision depends upon his knowledge, experience, and expertise. And same is the case here. So sometimes the forecaster has to consider certain observations as outliers. It may consider, it may not consider, and he may go by certain other situations. But if I compare the decision making by the objective methods and the subjective methods by this one, I'll say it is 80-20 nowadays. With the improvement in numerical modeling system, mostly decision is based on 80% based on the numerical model, supported by 20% with the knowledge, experience, and expertise by the forecaster. Now, with over the period of time when the forecast accuracy has improved, so people have thought that simple forecast is not sufficient. We should give some kind of impact-based weather forecast and risk-based warning. So for that purpose, what the people do actually, they convert the digital forecast available from a decision support system to a plain language forecast, which is called as end forecast. It goes to general public, disaster managers, and stakeholders. And at the same time, they add what are the damages expected and actions suggested for response actions. So that is impact-based forecast and risk-based warning. So it goes in text form, it goes in graphical form, and text graphics form, and nowadays also audio and video form. Then it goes to decision maker. So therefore, decision maker, when it comes to office and goes through the forecast, it is an end-to-end solution. He knows about the current status, he knows about the current forecast for next 3 days or 5 days, and also he knows about the expected impact and expected risk and the suggested action. So he has to just take the action based on that. But while doing that, there should be continuous coordination and interaction among the forecaster and the something is coming. Okay. So while doing that, there should be continuous effective coordination among the forecaster and disaster managers. Because sometimes it may so happen that forecast may vary from morning to evening, and at that time disaster manager has taken already action based on morning forecast, and evening forecast is changing a lot or changing to some extent, so he may be confused. So therefore, whenever there is any change, always there should be coordination so that both are in confidence to each other. So while talking about the South Asia, you will see that we have come up a long way. There was the history, for example, in 1970, not far behind, in 1970, around 300,000 people died in Bangladesh because of one cyclone that is called as Bhola cyclone. That cyclone crossed or hit the Bangladesh coast near Bhola Island, and 300,000 people died. And it is, as an expert team in WMO, we found that this is the worst disaster in the recorded history of the world, where 300,000 people died. That notorious history has been created in Bay of Bengal. But the good thing is that over the period of time, now we have been able to erase that notorious history. And at present, if any cyclone goes to Bangladesh or any country in South Asia, you will find that the death toll can be reduced. It is impossible because of overall integrated action by the states, country, and the international agencies also. But overall, the early warning, which is the first step towards the disaster management, has improved over the years. So similarly, there is another recorded history also, that is hailstorm. So Moradabad is a place just nearby to Delhi. It has got recorded notorious history of around 250 people died due to one hailstorm. So in a particular day, there was a marriage procession going on, and there was a hailstorm. People died, buffaloes, cows, all perished. So that notorious history again goes to us, and we know till now also the mesospatial events like hailstorms, thunderstorms, lightning are still challenging. But of course, number of deaths have reduced. But still, if you consider lightning, every year in India, for example, around 2,500, 3,000 people die. Same is the case if you just look at various countries in South Asia. It's very prone, especially eastern part of South Asia is very prone for the lightning and thunderstorm activities. So there is still scope, therefore, to minimize loss of life due to the mesoscale weather events like thunderstorms, hailstorms, and squall. So lightning similarly has the dual record. That means Eastern Africa and Bangladesh are notorious for death due to lightning. That is, highest death due to any one lightning strike has been recorded in Bangladesh. Therefore, what I want to say that the South Asia is very prone for the natural hazards and weather-related hazards, and there is scope still to improve. So what we do actually, there is a regional mechanism. There is a collaboration and cooperation among the countries in South Asia, Southeast Asia, and the Middle East. And India, for that purpose, acts as a regional specialized meteorological center. There is exchange of meteorological observations with globally and also countries in South Asia. There are regional climate centers located in IMD, which are catering to the services of all these countries in this region. We provide capacity building through the training purpose, R&D, whatever we carry out that is shared to all these countries. And of course, climate change, we have got a special center in Ministry of Earth Sciences, and all these data are being provided. Polar research is also carried out here with the support. And as I was telling, we have got regional specialized meteorological center in Delhi for the purpose of severe weather, for tropical cyclones, flash flood for South Asia. So just look at how the collaboration works for observational systems. You can just see that weather has no boundary. And if you do not have observation from Bangladesh, for example, or Pakistan, for example, or Nepal, for example, you cannot have a realistic view. Similarly, if you don't have observation from India, Bangladesh cannot take action with respect to floods. So therefore, there is a regional cooperation which is essential, and through WMO network, there is a cooperation, and also through SARC network, there is a collaboration among all the countries with respect to surface observations, upper air observations, marine observations, aircraft observations, satellite observations, or even radars, which we have put up, around 34 radars we have put up across the country. The neighboring area of all the South Asian countries also benefit from those radar. And we have got INSAT 3D and 3DR, which is also helping to these countries. And all of us know that satellite data plays a dominant role in weather forecasting. And by providing INSAT 3D, INSAT 3DR, and certain polar orbit satellite data, India plays a dominant role in this region towards collaboration and cooperation. About 20 to 30% accuracy improvement or accuracy improvement in weather forecasting globally occurs because of the satellite data. So satellite data plays a significant role. So we have these satellites. What we do actually, we not only provide the satellite INSAT 3D, INSAT 3D-R, but also all international satellites which are available over this region, we collect the data and share the data for numerical modeling purpose to all the countries and all the centers. Similar, this is the radar I was talking about. There are 34 radars, and there are radars in the coastal areas and the hilly areas also, and neighboring countries there for Nepal, Bhutan, Pakistan, Sri Lanka. They get the favorable information from the radar network of India. And of course, there are certain radars in Bangladesh. When you take observations and provide forecast to Bangladesh about the cyclones, certainly we look at the radar of Bangladesh. So therefore, it is a mutual cooperation which helps to better understand and predict the various types of severe weather events. Now let us talk about the telecommunication. Yes, we have come up a long way. Actually, in 1974, if I just look at the Philips system where few kilobytes of data were being exchanged. But now you have got the system in India, which is a regional telecommunication hub, which is helping all these countries to collect the data and provide all this information. So what I want to say, the country is celebrating now 75 years of independence. So after the independence, there has been significant improvement with respect to various types of early warning systems, especially hydrometeorological hazard early warning systems. And just I have shown you in the previous slides, the satellite support has been there since 1982, with the beginning of INSAT 3D and radar came up in 1970s, and it is continuing now. Similarly, the communication system is also being supported to all the countries in this region for exchange of data. So this is the network of regional telecommunication hub by which we connect with all the institutes in the region and also various countries in this region. There are dedicated links with some countries, and there are also global telecommunication links with different countries in the region and globally. So with all this, what we do actually to support the South Asia with the weather forecasting and management of hydrometeorological hazards, we go for a seamless forecasting system. We have got nowcasting, which provides forecast up to 6 hours. We've got two nowcast models, which covers the area of South Asia to provide the forecast on thunderstorms and associated weather and heavy rainfall also. Then we have got the cyclone-specific model in short to medium range, which can provide forecast for cyclones. And we have got global models and regional models, which cover the entire South Asia, Southeast Asia, and Middle East. And the extended range forecast is provided every week, which also covers South Asia and valid for next 4 weeks. Seasonal forecast is provided by Regional Climate Center, and it provides the every season, every month forecast for South Asia. And there is a forum called as South Asia Outlook Forum, Climate Outlook Forum. So there's a scope, all the countries meet each other, and they decide and issue the forecast for South Asia. Now, so as I was telling you, these are the global models. We have got two global models. One is based on gridded framework, another is the spectral framework. And with this framework, we provide the deterministic forecast. Accordingly, we have got two ensemble forecasting systems, and both have resolution of 12 kilometers. And it is a very good resolution if you look at the other global models available globally. So we have also a number of dynamical statistical models for various purposes for management of early warning hazards. So all the outputs from all these models are being provided to various countries in South Asia in data form. Digital data are also being provided, and image products are also available in the website. So based on all these things, we finally provide forecast and early warning up to 5 days for various types of natural hazards or meteorological hazards. And there is outlook for next 2 weeks, but realistically speaking, globally, the early warning is available up to 5 days. Beyond 5 days, there is no accuracy in early warning globally at present. So most of the countries in development also go for warning up to 5 days. So this is the extended forecast. I think Dr. Patnaik will discuss in detail afterwards. This is just an example that how it is covering South Asia and it is benefiting them for management of early hazards. So just imagine how much data we consider while going for global modeling system. So you can imagine how the data volume which is being handled. It is possible because of the dedicated telecommunication system, and also it is possible because of the high performance computing systems. So with all these data, all these models are being run, and at the same time, we have got a geospatial platform for comparing, comprehending, analyzing various types of observational data and model data, as I was telling in the beginning, by the forecaster. This is just an example of the products available from our decision support system. And with this, in a geospatial platform, very specifically in a ground manner, the informations can be generated. Now, coming to specific applications for the South Asia, the India Meteorology Department acts as the regional specialized meteorology center for tropical cyclones. It provides guidance to 13 countries in this region covering Bay of Bengal and Arabian Sea. So all these countries have benefited because of the early warning of the tropical cyclones and depressions. You can see here. So we have the round-the-clock watch for this purpose. We provide support every day, and when cyclone is there, every 3-hour forecast information is provided internationally. We act as a tropical cyclone advisor to all these countries. And also we act as a tropical cyclone advisory center for civil aviation, international civil aviation occurring over South Asian region. All flights and all meteorological watch offices and airport authorities get the information whenever there is a cyclone. Otherwise also, the information is being provided by India Meteorology Department. And we issue a special bulletin called a SIGMAT as and when there is a disaster situation arising in any area in the meteorological watch office of the country. So we also act as this RSMC for SWFP, that is Severe Weather Forecast Program. It includes heavy rainfall, it includes the strong winds, thunderstorms, waves, swells, etc. over this region. It also goes to all the countries in South Asia. So this is just an example of what we provide in the Southeast with respect to tropical cyclones. You can see the track and intensity forecast at the top, and below you can find out wind, flood, and surge forecast. All these are being provided in a geospatial platform and impact-based forecast and risk-based warning system. So we provide this system at least 3 hours in advance, which is called as cyclone watch, and then after it becomes cyclone alert and cyclone warning. So if you look at the excellence early warning system, how it has evolved over the years, you will see that error has reduced continuously over the years. And at present, if I compare the error with National Hurricane Center, you will find that our error is at par or slightly better than National Hurricane Center in certain cases also. And JMA and other agencies, if we just compare, our forecast accuracy is far better than any other country. So therefore, that has been a significant improvement which has enabled South Asia to minimize loss of lives during last 10 years. If I just look at the number of deaths due to the cyclones in the last 10 years, whether in India or outside, the right-hand side picture shows the cyclone death in the different countries in Bay of Bengal and Arabian Sea region. You will find that there is no such cyclone where the death has exceeded 100. So one figure you will find 135, but that is a combination of two countries, that is Bangladesh plus Sri Lanka. Therefore, there is no such cyclone which has hit the coast and caused a death more than 100 in last 10 years or 12 years, starting with 2010. Now coming to further cooperation in the marine activity. You know that people talk about a blue economy. Deep Ocean Mission has been taken over by many countries, and also in India has taken off the Deep Ocean Mission. The objective is to harness economy from the sea, improve the economy from the sea. There are now many stakeholders. I think we do not know. Since we are located in land, we do not know what is happening in the sea. Actually, if you find, by chance, if you go into sea, you will find that there are many players. It is crowded now. There are a lot of players and for various activities, starting with the fishermen. You have got the small ships, you have got the big ships, and you have got the ports and oil explorations and many others. So for all these purposes, you need to have the forecast. So therefore, what we do actually as a regional center here, we provide the sea area bulletin every day, twice. We provide the information about the weather conditions over the sea. It includes the rainfall, winds, waves, and significant pressure systems, swells, etc. So in case when it becomes a depression, a bulletin number increases, it becomes 3 times, it becomes cyclone. Every 3-hour bulletin goes for the marine community. It goes to marine community by a dedicated satellite channel. That also IMD pays for that, about 5 crore per year. It goes to Inmarsat. And this Inmarsat, the International Maritime Satellite, is used to provide information to all ships. And ships should have the receiver, and ships have this receiver, and they get all these things. Now, similarly, we provide sea area bulletin for global maritime distress safety system. India is a part of global maritime distress safety system. We provide all these informations to those who are registered with the global maritime distress safety system. Then coastal weather. As you know that coastal weather is very important because a lot of activity goes on the coast, especially the fishermen, poor fishermen, and the trawlers, ships, etc. So for this purpose also, dedicated bulletin goes every day twice and during cyclone period 3 times, and depression period, cyclone period 8 times, depression period 3 times. So this was earlier only the textual message, but nowadays you can have the textual plus graphics message in GIS so that exact locations can be identified and action can be taken. So we have the SWFDP South Asia, as I was talking about. This also provides the textual bulletin, graphics bulletin, and impact-based information. The countries are Bangladesh, India, Maldives, Myanmar, Sri Lanka, Thailand, Bhutan, Nepal, Afghanistan, and Pakistan. So all these countries, the area of responsibility is shown in dotted line here. And one of the example of the graphic product for the winds and rainfall and waves are shown on the right-hand side. Similarly, there has been cooperation with respect to hydromet services, flood forecasting. So you know there are 3 types of floods generally which affect South Asia or any other particular region in the globe. One is the riverine floods. The riverine floods occurs in this region mainly the transboundary floods. So you will find that many rivers originating from Himalayas. So therefore you need data from Pakistan, you need data from India, you have data from Nepal, Bhutan, Bangladesh. So if you really plan to manage the riverine flooding in this region. So therefore there is a good cooperation, there is exchange of data, but remote sensing helps a lot because the data sparse region, you cannot take observational data. So Insat 3D provides these informations which are being used by all these countries in this region for management of riverine floods. Now next comes the flash floods. The flash floods are very dominant in the hilly areas like Himalayas, northern parts, and also flash flood occurs in the Western Ghats and Eastern Ghats areas. So these flash floods are very dangerous. It leads to sometimes the mudslides, mudslips, sinks, etc. A loss of life is very high due to this. So what we have done actually, we are preparing a South Asia flash flood guidance system. It provides every 4 kilometer the forecast for entire South Asia, and these are communicated 4 times in a day, valid for next 6 hours, next 12 hours, and next 24 hours. It provides the flood depth, flood threat, and flood risk over a particular watershed. There are about 30,000 watersheds in India, and according number of watersheds in other countries also. So if I look at the mesoscale events like thunderstorms, yes, quite a few years back, we started with the SARC storm project, where we are providing with the regional center, providing guidance about the occurrence of thunderstorms in the SARC countries. So now it has stopped, but again, it is being revived by SARC Disaster Management Center, and we'll be happy to provide. But nevertheless, if you just look at the thunderstorm prediction models, which are being generated by India, you will find that it covers the South Asia. For example, I have just put up here the lightning forecast, which only about 5 countries in the world provide lightning forecast, and we are one of them. On the left-hand side, one of the examples is lightning forecast by the WRF model. And on the middle, that is actual lightning. It is a very good forecast model. It has come up a long way, but still there is scope to improve further. What I want to say that this model is covering the South Asian region, and by that way, they are benefited. At the same time, India has got lightning detection system. The lightning detection system with the lightning network, as you know that it is just like the earthquake monitoring system. So therefore that lightning network helps to detect lightning other countries also. All the countries in South Asia get benefit of the lightning detection system of India. The third is that based on satellite also we have got lightning detection system. We utilize, Insat 3D does not have lightning detection system, but we utilize other satellites and accordingly we issue, and this information is also available to them. We have come up with a system called RAPID based on satellite, and that is also being used by them to provide the guidance to all the countries in this region. This is a new phenomenon, that is impact-based forecast and risk-based warning, what I was telling you. We have just started in the country last 3 years, and we are providing capacity building support to the South Asian countries and countries in the Bangalore Arabian Sea. So we will be very happy to extend our hand-holding to any country, those who are interested to implement the impact-based forecast and risk-based warning for, and by that we also will learn, we will have the lessons learning from each other. So impact-based forecast will go for, actually it not only deals with the weather forecast, but also deals with the various types of other parameters like say socioeconomic indicators, then digital elevation, then you have got the various geospatial data, and also you need the secondary hazards and tertiary hazards data. For example, if you have got heavy rainfall impact you are going to give, you should have also information about the floods, the landslides, etc. So therefore we are working towards this direction to improve further in the country, but we will be happy to work with other countries also. So this is the geospatial service available now. All severe weather events in the country are now available in geospatial format. Please visit our website, mosam.imd.gov.in, you can find out all geospatial platform for any type of severe weather hazards. So this is the list, and this list is going gradually. Now I'll just come to way forward. What I want to say that South Asia has improved and has learned lessons, and there has been handholding, there has been cooperation and collaboration, and IMD has played a dominant role to provide support for a multi-hazard early warning system development and applications in South Asia. But still there is scope. If we just look at the value chain is like this. It starts with the observations, the modeling, forecasting, severe weather warning, sectoral applications. In this value chain, if you look at South Asia, what I was telling that is a data sparse region, there is a need for investment. There is need for technological investment, so that you should have very realistic data set. Optimal data network should be available in each country in South Asia, except India. If you just look at various countries here, to some extent Bangladesh we have very not that up to mark system, and at the same time Bay of Bengal and Arabian Sea. So therefore there is scope to improve the observations and according to the modeling. This, for example, with HPCS we are providing model guidance, but the dynamical statistical downscaling in all these countries could be possible, and for that purpose capacity building of the people in these countries are essential. So therefore again there is need for investment, collaboration and cooperations. And for finally the severe weather warning, whatever we are providing, that will be more granular, etc., further improve. Can be on sectoral applications, as I discussed earlier, also needs improvement. Considering this data sparse region, what we have done actually, we have gone for the crowdsourcing. So similar crowdsourcing also have been attempted by Nepal, and some other countries also can attempt that by crowdsourcing, because we have a large population in the South Asia. So that should be taken advantage of. We can go for crowdsourcing, so that instead of going for so many investment in instrumental observations, we can at least have realistic observations with respect to various types of weather. So day has come for utilization of artificial intelligence and machine learning. So people are thinking about the dual engine concept, that numerical modeling plus artificial intelligence and machine learning should go together. They should complement each other in decision making and improving the forecasting of hazards. So digital forecasting, gone are those days when we are dependent only on the subjective interpretations. So gradually the objective methods are coming up, and they will come, I am sure, within the next 10 years. There will be no role for forecasters to give the forecast. The subjective approach for 20% will reduce, and it will be completely digital. So how will it be possible? It will be possible only when there is a dynamical statistical approach along with the numerical modeling and AML, etc. I hope that is also coming up in near future. We can see the day. So, I will conclude here that there is scope therefore for partnership and collaboration in South Asia further, which has been realized so far, and to take it forward to minimize loss of lives and properties. So thank you. I'll go. Stop. So any question? Anybody wants to have any questions or comments? Yes, please.
Good morning, sir. So I want to ask something from the cyclonic activity. So you know that there are several parameters which determine the outcome of the cyclone. So I just want to know what should be the time frame for to use the data set of different climatological parameters, so that we can run the model and determine what could be the outcome of cyclonic activity in the near future.
See, as I was discussing about the seamless forecasting, it starts with season and ends with a few hours. Okay. But as far as cyclone is concerned, over North Indian Ocean, there is no skill in seasonal forecasting. So you can find seasonal forecasting Atlantic and Pacific, but there is no seasonal forecasting. Even R&D also not very visible, because people know that variability is quite high. We have got only 5 cyclones, and that again includes Bay of Bengal and Arabian Sea. That again includes 2 seasons, that is pre-monsoon season, post-monsoon seasons, and frequency variation from year to year, season to season is quite large. So that variability is so high that seasonal forecast has not been possible so far, even if there has been some trial. Now, therefore, we do not go operationally over any seasonal forecast. Then comes the extended range forecast. Yes. Since 2018, we have started extended range forecast. That gives only the probability of genesis. It does not talk about the track or intensity. It just says whether there will be a genesis or not during next 1 week or next 2 weeks. That has been very successful. So this genesis forecast gives a very good idea to the disaster managers for preparedness. So every forecast has its own value. So with that extended range forecast for 2 weeks, which is in place, say for example, now current depression, so we predicted it. That there will be depression over Bay of Bengal. One is over, another one I was expecting, and Arabian Sea also one depression is going to form today. So the type of genesis forecast helps the disaster managers to be prepared in 10 to 15 days term for general taking stock of the situations. But another advantage, the most important advantage, we cannot appreciate or understand because we are in Delhi or we are in the landmass, is the fishermen and the marine community, offshore installations, oil explorations. So all these people are just hungry for information because nowadays the fishermen are not confined to the coastal water because fish catch is not so high in coastal water. They want to go into deep sea. Once they go into deep sea, they take time, sometimes 10 days or 7 days to go and come back. So therefore, if they can get some information that in this particular area, there is some possibility of genesis, because for fishermen, 45 kmph wind is dangerous. So therefore, genesis starts with depression where wind is at least 45 kmph. So by that way, that external forecast helps to other stakeholders also. Then comes the short to medium range forecast. And every day we give a tropical weather outlook telling that whether there is a probability for development next 5 days with say different probability scale, low, moderate, high, etc. So that again gives the genesis and some subjective statement that what is the track and intensity. Then when depression forms, then we go for track and intensity forecast valid for next 5 days, and their real action starts. So up to 5 days, as I told, globally is the case where warning is more actionable, and accordingly we go for that. And as for the standard operation procedure, the cyclone 4-stage warning system in the country starts 72 hours advance of the commencement of adverse weather. So therefore, adverse weather commences when the cyclone reaches the coast. So 3 days before, at least we should provide that. But sometimes it may so happen that development takes place near the coast, you don't have 5 days time. So standard operation procedure is that 5 days and 3 days in advance cyclone information should be provided, the past information should be provided. But there are certain cases when it can be near the coast. So immediately, as and when you find the information, it should be immediately told to the disaster managers. Otherwise, as a practice, it is 72 hours in advance pre-cyclone watch is issued, and it is reliable. And we have come up a long way in that direction, which has enabled to minimize loss of lives and properties. It is appreciated globally.
Another follow-up question
Mhm.
I ask. We know that in this sort of model, there are a lot of uncertainty associated. So what is the current scenario, and how you're doing when you are running this model, and what is your insight in your future to increase this accuracy?
Yeah, as you told that every model will have its own limitations and there will be uncertainty. But uncertainty is reducing over the period of time. Okay, so if you look at the track forecast of the cyclone, we introduced cone of uncertainty that gives the uncertainty track. It was introduced in 2009. December 2008, we introduced first. And now, if you just look at every 5 years, we go on changing the uncertainty. The cone of uncertainty, diameter of the cone is reducing by about 20 to 25% every 5 years. So that means the forecast is improving accordingly. So how is it possible? It is possible because the cone of uncertainty what we provide, that is based on the multimodal ensemble. The multimodal ensemble guidance is utilized and historical cone is prepared. So the track therefore is very much dependent upon the improvement in the multimodal ensemble. We do not depend upon one model. The concept is that single model will not be successful. Even if the best model you consider, this morning forecast may change in the evening. So therefore, what we do actually, we make a consensus. It is weighted average multimodal ensemble, which is utilized to take care of the most probable track and to take care of the uncertainty track. At the same time, also we have got R&D with respect to single model ensemble prediction system, where we have got 20-member unified model and EM-EPS and also 20-member GEFS. So these are also considered to find out what is the spread or uncertainty in the track. And globally also, multimodal ensemble is very successful compared to any individual model. So if you talk about the future, yes, there is scope for improvement in the future because still there are certain cases where models fail, and there are certain cases where the track, especially the recurving tracks, are not predicted well. Intensity is the worst case by the models. We do not have very good prediction of intensity by the models. So there are certain specific cases, rapidly moving cyclones or slowly moving cyclones or recurving cyclones. These are challenging by the models for the track. And intensity, especially rapid intensity, rapid weakening, these are challenging by the model. So there is scope therefore. So what is the scope then? There is scope to improve the physics of the model by have the data assimilation and by defining the physical processes and also by improving the resolution of the model. At the same time, the uncertainty can be taken care by the ensembling system. We can increase the number of ensembles, and accordingly we can have in-depth R&D to find out the best models based on which we can go for the final ensemble system. That is a grand global ensemble system. So another point is that there is need for diagnosis. Each and every model, those who are modelers, they should diagnose. Don't think that it is your model. I will tell you, we adopt WRF, we develop GFS, we adopt UMPS. It is not our model. Sometimes what happens, it crops up in the mind of the modelers that it is my model. So that creates problem. Therefore, by the time what happens, no, he wants to showcase the best cases. He does not showcase the worst cases. And accordingly, even if he understands the limitations, he does not explicitly say, he does not explicitly realize, and therefore the research gets limited. So that should not happen. As a good researcher, we should expose, we should discuss all the limitations first, and accordingly should find out what are the ways forward by that way. So collaboration in the direction is very much essential among the researchers in the region.
Thank you, sir.
Yes, please.
Sir, I wanted to ask if there is any way to forecast forest fires.
Yeah, forest fire forecasting has not started so far in the country, but there is scope, especially considering the fact that India is a deciduous forest region, okay, it's a tropical region, and usually there will be dry leaves in the month of February and March, and just like this year, the temperature will increase in the month of March and April, and that continues up to May, and ignition takes place. So therefore, there is a need for, or there is a huge scope, you can say, for understanding the forest fire and the region of the forest fire, and what are the natural processes, what are the artificial processes leading to the forest fire also. Usually forest fire, if you just look at the density, is more in Tarai area, that is Western Himalayan region, etc. And also you will find forest fire to some extent in the northeast also. But nowadays in recent time, I found that Similpal also in Odisha had the forest fire. So we have to see again whether the forest fire extent is increasing to different forests, etc. And that is the climatological analysis can be carried out. That will be the first guess towards the forest fire forecasting. Second one should be the cause and effect relationship. What is happening actually? What is the ignition temperature for different types of wooden trees, dry woods, and etc. And there is a lot of data for that purpose. India Meteorology Department is a huge data set. I am telling you, freely data can be provided to any research group if it is meant for research only. If it is funded project, I cannot help you, you have to pay. Or if it is not funded project, anyone interested to carry out any work, we will be happy to share all types of work through collaboration. Please collaborate. We are happy to provide all support for that purpose. So there is scope based on the forecast of temperatures in extended range, in short to medium range. You can find out whether it is probable that it will exceed the ignition temperature. If there is a probability of exceedance of the ignition temperature, then you can provide some kind of guidance. But of course, it does not depend only temperature. It also depends on the humidity, it depends on the winds, it depends on the past weather. So all this has to be taken into consideration. So one by one, it can be taken up, and it is a good area where we can start the forest weather services.
I have a question in terms of first the computing power, the high performance computing. So whether there are any opportunities for parallel processing for for these kind of models. And second is in terms of partnerships and collaborations. So whether you are doing some kind of not just temporal time horizon of maybe 1 year or so, but maybe 15 years, 20 years down the line.
Usually, I'll respond to the second question first. Usually, if you see last 3 years, the MOU, the Memorandum of Understanding with various academic and R&D institutes has increased manifold. And that is usually 5 years. and that is extended every 5 years. You can, after that, so there is no end. So you can go on increasing, and there is no data. And usually what we are doing, actually, we are making a place like situation that will provide all types of data support. All type, whatever. We have got digital data from 1901 onwards, all conventional data. We have got satellite data from 1980 to 83 onwards. We have got radar data, Doppler radar data from 2004 onwards, certain area, but now in recent times we have got more data. So all this data can be provided, and that MOU, it is no time limit is not, but of course, collaboration should be there. It should be acknowledged that this is the IMD data which are helping to carry out this work. And regarding your first question, parallel processing, yes, MOS has given some kind of support to the academic and R&D institutes. And but however, what happens now, the value chain I was talking about, the demand and supply chain is so high that operational forecast needs so much recruitment that is not available also. So we are going to improve our high performance computing system from 10 petaflop to 30 petaflop. There is also scope for availing and the computing power. At the same time, monsoon mission phase 3 is coming up. So there is scope to submit the proposals, and through that also you will have the support, even the financial support also that is coming up. And sometimes we float various types of proposals through Ministry of Arts and Sciences, just like AML proposal, it was floated, and Thunderstorm proposal, it was floated. That also can be carried out. The last but not the least, I will tell you that National Supercomputing Mission, under that also you have got academic and support towards the computer. So there also, I was just going through in the STIF concept. So there are many institutes, IITs, who have been provided with the supercomputing powers, and it is understood that they should also share those who are interested. So you can contact CDAC and many other agencies for this purpose. I think you will have some support. Okay, so thank you very much. Wish you all the best.
As sir has to leave, on behalf of TIFAC and IASA, we would like to felicitate you for being honorable speaker of the day. For that, I would like to call KC Gowda sir to do the honors and provide the token of appreciation to the sir. And I would like to call DK Patnaik sir to take the chair.
So very good morning. So we will just continue the session, and as you know, it is a very tight schedule now. So we'll straight go to our next speaker. I think it is Professor Bimal Mishra. So he will be joining virtually. So may I request Dr. Bimal to kindly restrict your talk around 8-9 minutes.
CSIR located in Bangalore. So our basically approach is for the multi-sectoral application for climate and weather informatics. So you use the supercomputing. I am from the climate group. So our vision is to provide scientific and technological solutions for the scientific and industrial benefit through mitigation of adverse impact of climate and environment. So we work on several aspects and several mission of Government of India like Samarth Bharat, Sashakt Bharat, Swasth Bharat, etc. So coming to this weather and climate it's going. It's moving. Yeah, so this is the approach where you can see we have the domain knowledge expertise starting from agriculture to health and disease to climate system. So we adopt those things for other processes, we identify processes, then we have some of the data product, we collect data from other agencies, then we design the database, and we have a strong academia linkage. We have our own academy of CSIR. And therefore, we also believe in capacity building, outreach, and innovation of integration. We have so many success stories. So coming to this kind of conference, it is very, of course, obvious to introduce you the CSR multi-scale platform. So we have the hydrometeorological disaster platform where we have the ample of general circulation model and mesoscale model configuration. Those are all in operational setting as well as in research mode. And we do the data assimilation by inducting various sources data to improve our forecasting capability. We do the multi-model ensemble forecasting as mentioned by Professor Mahapatra in the earlier talk, and we believe in the objective debiasing because all the model have its own bias. So we have developed our own techniques on algorithms, and of course, being the Institute of Fourth Paradigm and Data Intensive Research, we do the artificial intelligence and machine learning approach for the prediction of weather and climate informatics. And of course, our another strength is we do the user specific. Therefore, there is a term what I have mentioned, the GIS interfacing. Finally, it also gives us the continuous validation because your forecast and hindcast depend upon the continuous validation. So we have all the structure. For example, our monsoon forecasting is 40-year validation. We do all these extreme rainfall event, cloudburst event, heat wave simulation, tropical cyclone simulation. We believe in the rigorous validation and the assimilation technique. We have several groups who are worked on this thing with more student powers. So these are, as you know, different issues in early warning of hydrometeorological disasters. So keeping all this in mind, we have to believe and how to do the prediction for a systematic approach we adopt. So if you see this, there are the use of numerical weather prediction for a high impact weather warning because my emphasis will be on high impact weather warning because one thing is forecasting, but the second part is warning. So how to translate from forecast to warning, that is the important aspect what we should discuss in this systematic application of this conference. So you see the forecast, one is the outlook or watch warning, which is generally done by global model, which is more than 10 kilometer resolution. And the input, as you can see, with 6-hour cycle, we do use the GTS and various satellite, but it's coming to the regional convective because when we talk about this thunderstorm, cloudburst event, those are very localized and very what we call short duration, high intense event. So to do that kind of thing, we need the regional and convective parameterization model. Therefore, you see, and another approach is how to warning. So for warning also, we should go to the resolution which is less than 1 kilometer. So we have the all facility of high performance computing system. So where we do all and ensemble and approach of data assimilation processes for this kind of warning. So finally, there is a need of the blending numerical with the prediction and the observation based, which can improvise the nowcasting, which is less than 1 to 2 hour kind of thing we can see. So these are some of the examples where we do the model configuration. This is, I am showing one of the case study. So when we do the WRF model domain, we go for the regional specification. You can see here, for example, the Uttarakhand cloudburst region. So we do the modeling configuration domain in northern side, what you can see the left side panel. At the same time, suppose we want to study the impact of urbanization on the Bangalore urban extreme rainfall. So that you can see in the right one where we have taken the Bangalore and another is the Uttarakhand in the left panel. So these are some of the simulation what you can see with different domain. The internal what we call domain 3, you can see the rainfall is well captured. The top one is the Mumbai, Bangalore and Chennai heavy rainfall. So this shows the capability of the high impact warming, basically extreme rainfall of urban city, how it is being captured well in the forecast setup by integration with the satellite data assimilation technique along with the multi-source initialization and running the and simulating the model in operational mode also. So if you see another point here, I want to emphasize, we do update our knowledge. So what we do, we run the model. If you simulate the model with old data taken from USGS, it will give one simulation, but actually there are several land use, land cover pattern has been changed. You can see the left one is 1992. The red patch is only little. Red is nothing but urbanization. So this represents the Bangalore city. But you see the right one, the red patch has been increased 25 years, threefold increase. So therefore, if until unless model knows that there is a more urbanization, earlier lake has been covered with the that became a stadium now. So that representation will affect your simulation, and in the process it will give the clear and accurate kind of prediction. So this thing also we integrate with our ISRO Bhuvan data. So integrating that, we do the prediction kind of thing. And you can see these are, as I mentioned, in the rigorous validation, we do the validation with the India Meteorological Department data at the same time, because we are from Karnataka. You know, Karnataka State Natural Disaster Management Authority, which is very rich in data, because they have put the automatic rain gauges at every taluk or every village level. So you can take and you can go to your high resolution prediction. You have validated. So this is one of the example where we have done. Then coming to the point of thing, this is, as I told, the Uttarakhand concept. You can see the different panels. The left panel represents the India Meteorological Department real observation data, which is then second panel shows the satellite measurement by the TRMM mission. And you can see all these in right hand three, these are the different setup, because the model setup depends upon how you are going to get the credibility of your prediction and accurate. Therefore, you can see one is the control experiment, then test and test 2013. That means last two panel represents the test of 2006 land use, land cover representation, what we called in our language boundary condition. But if you go to the 2013, the more accurate and nearly close boundary condition, then it has resulted good result, which is well compared with the IMD and other sources. This is also, you can see, not only capturing the extreme rainfall event, also it is very important to do the unusual rainfall which comes. For example, northeast monsoon extreme, what we saw in 27 November and 2nd December in Chennai, that is also well captured. So these are some of the examples what we have done. So apart from rainfall, another parameter is very important is the wind. So therefore the associated wind structure also here you can see the left is 850 HPA and upper is the 200 means height wind, which is also captured, because that can also again translated into different disaster parameter, which will be helpful for the user sector. This is one of the other example of Bihar where we have done the thunderstorm activities. So if you go to this kind of thing, so more important is the cloud simulation. So using all those technique, we have developed the modeling framework for the cloud prediction. Using that, we have running a National Mission of Himalayan Studies project, where our study area we have taken the Beas River basin, and even the Beas River basin we have able to predict. These are the different preliminary results. The left represent the IMD observation, and right one the model simulated cloud burst created rainfall, which are well captured by the model. And another aspect, as I told, this session is demanded for heat wave, and you can see I am just showing one example of the Odisha, and in the state of Odisha how this has been captured before 72 hours, the prediction of maximum temperature scale. And you can see the red color indicates 46 degree, which is well captured because we have the calibrated and configured modeling framework, which is being used by the supportive data assimilation for the greater analysis. And more than that, at a location you can see the extent up to what latitude, longitude, that extent of heat wave extent, that also we can develop. So, but here my emphasize more impact representing the WMO high impact weather team. I can say there is a need of to gap these bridges. You can see first one is the observation, then we come to weather forecast where we run the weather modeling. But the very important is how to convert into that weather prediction into hazard forecast. For that you need the ocean, land surface and pollution monitoring, that we are being integrated. And again, after getting hazard, you have to translate, because this conference is about the system policy, so you need to translate into impact forecast, how much that kind of hazard is going to impact on our land mass. Then after that you have to accordingly issue the warning, and for warning again you have to develop the communication system, messages, media including social media, and finally we get the behavioral psychology. So based on this gap, just now we published a book by WMO towards the perfect weather warning, where we have seen how they are going to work together. So therefore you see all these bridges what I showed, that gap is in taken care. So this is my last slide, which says there are two components. One is research and development. Here more researchers are there, and top one is the operational. By combining this only we can go for the good policy development. But if you can see the research development starting from the requirement of high resolution data to research modeling parameterization you can see in the lower, but there is a link of operational monitoring network what presented by IMDDG. So there is a time to synchronize and work together. So therefore, if coming to these sessions view on high impact weather research, we need action plan for disaster risk management. Therefore, three component. One is the identification, reduction, and transfer. Therefore, my last suggestion will be you have to identify the good practices. You have to implement all these early warning system sharing and how success it was coming into value chain. Finally, you have to document all these good practices which can enhance the policy documentation and for a better sustainable and disaster-free or disaster mitigated India. Thank you so much.
Thank you, Dr. Gowda.
Yeah.
Actually, we can take the questions in the free time if there is, if you don't mind, because it's a very tight schedule. Yeah, very specific question, you have?
Yeah. Yes, yes, we do that. Yes, we work on air quality forecast also. We can discuss about the time. Okay, yeah. Thank you. Guys.
We'll go to now the next speaker, Professor Asutosh Sharma. Please speak.
Risk. I think we have some other persons who will be speaking about, on climate extreme. So I'll skip that part. I'll directly jump to the second part where I'll talk about flood risk. Last two speakers have emphasized slightly on application of machine learning, and that is what I will focus on. I have been working in this field for a while now. We have been developing some machine learning based tools for flood risk mapping or for stream flow, large scale stream flow predictions in the country. So my main focus will be on that part. So please don't mind. I'll be skipping next few slides, directly jumping to this part. Okay, so one of the extremes, main extremes in hydrology that we have is floods. So the topic that I will be talking is how we can use machine learning, firstly in flood risk mapping, and secondly in large scale hydrological forecasting, wherein I will be discussing about some deep learning models that we recently developed. Now, one thing that we know when we say flood risk, it is a combination of flood hazard, vulnerability, and exposure. We can make something called flood risk maps, which is nothing but a multiplication of flood hazard map and flood vulnerability map. Flood hazard map further has different factors that we account for. We overlay them into a GIS platform. We assign different weights to different factors, and then we get a flood hazard map. Same we do with the flood vulnerability map. Again, we could consider different factors which we multiply, which we assign some weights, we multiply them, and then we get a flood risk map. Now, there is one issue with this approach. What we have been doing so far is that we assign these weights based on some expert opinion, or based on the knowledge of the forecaster, and that is something which the first speaker was emphasizing on, that we have to move towards the digital forecasting. We do not have to rely anymore on the expert's opinion. And that's what we try to do here. We try to incorporate machine learning here, where machine learning can help us in identifying these weights. It can help us in telling us which of these factors have more weightage in terms of hazard or in terms of vulnerability to of the floods. So what we did, this is the overall methodology. We used one machine learning based model called random forest model. We use all of these factors as input to the models. The model was asked to make predictions of the flood risk maps. Initially, it was compared with the two-dimensional hydrodynamic model to make sure that the machine learning model is trained well. And then later, we use this model, the trained model, to get the weightage for different factors, and then which were finally used to get the flood risk maps. I will not go into the details of what machine learning model we use. The name was random forest algorithm. But these are some of the results that we got. What we found that the model was able to accurately predict the flood depths, which we can see in the map here. The R-square was pretty good at 0.98. And on the right-hand side, we see the relative weightages that were given by the model to different hazard factors as well as different vulnerability factors. The blue ones are the hazard factors, red one are the vulnerability factors. And we got the final flood map. So this is a flood map that we found when that we got after we assigned these weightages to these different factors. Now, the interesting thing that we are trying to do now, we have, for example, now we are having a machine learning model. The advantage with machine learning models is that they can be easily molded, they can be easily automated, which is a drawback between our physically based or process-based models. So what we are trying to do is we are trying to create an automated system where this machine learning model can be automated, can be automatically given some real-time information about the rainfall or soil moisture. And this machine learning model can help us in producing real-time flood risk maps. Still, we are trying to figure out how we will do this first part, wherein we will integrate it with some ground-based observations or with the satellite-based observations. But if we can do that, one advantage that we will have that this can, as this is now can be easily transported to a cloud-based platform. So this can be easily used to give some web-based services. For example, we can easily integrate this with the alert early warning systems where these models can automatically get the rainfall data sets and can automatically send some alerts. The second, I'll move to the second part. Now, this study that we did, as you see, there were small maps of the one particular basin I forgot to mention. So that was lower Narmada basin. Later, we thought that what if we can build a large-scale hydrological model with the machine learning? So far, if you see, we have some large-scale hydrological models. ISRO has been doing something. They have recently launched their portal where they are providing large-scale hydrological forecast. But the problem is that large-scale, those models, they are very rigid again in nature. If you have to integrate them with some real-time information, they will be very difficult because they need information into a particular format. Further, now we have large amount of data sets which is coming in from different sources. We have radars, we have ground-based observations, we have satellite precipitation products. Now those data sets can also not be directly integrated into a process-based model. So what we try to do, we try to build a ML-based model, AI-based model to predict stream flow at a large number of catchments around the country. Now this map that you are looking at is the map of the India, and it shows the catchments that we are considering for this particular case study. So these are 55 different catchments. One thing that we did carefully is that we selected catchments in such a way that they fall in different climate zones. Also, they are of different sizes and they have different land cover characteristics. Why? Because we want to create a robust model which can be transported or which can be transferred to the other basins also. Now, we do not have any such dedicated data on such large number of basins in India. So first step was that we created our own data where we had some time series of meteorological inputs like precipitation temperature. We had some static attributes which represents type of soil, land use, land cover, and other such attributes. Then what we did, we trained our model. So in this case, the ML technique that we use is called LSTM, long short-term memory. And these boxes that you are seeing on the top, these panels, they show the results that we are getting in this case. What we have here, we have these four panels. Each of these panels represents different set of watersheds. For example, the first one is perennial rivers, second one is non-perennial rivers, third one is large watersheds, the fourth one is small watersheds. So we are clubbing watersheds differently just to analyze the results, although we had one single model which is running over all of these watersheds. So as you can see, this is LSTM, which is shown as this blue box. LSTM model performed fairly well and the predictions that we are making at a daily scale. So this is daily stream flow that we are trying to predict. As you can see, the median NSC that we are getting over these watersheds for this LSTM model is around 0.5, which is fairly good, but again, it is not comparable to the state-of-art physics-based models that we have. Whereas we further improved this model, we did something called data integrated LSTM, where we are now feeding previous days stream flow as an input to model to make the predictions of the next day. And then we could see that the model's performance improved significantly. Now it is touching somewhere around 0.7 median NSC for each category of these basins. Now, then we compare it with some state-of-art models in or studies in the literature. We compared it with weak model, SWOT model, and another weak model study on the monthly scale. These are not our results. We took it from the literature, some of the recent studies, and these are shown here, A, B, and C. So A is for when we compare it with WIC at daily scales. B is when we compare it with SWOT at monthly scale, and C is again WIC model at monthly scale. Now, one thing that you will see clearly that in each of these cases, our LSTM model is somewhat doing as good as process-based models. In some cases, it is improving, but the DI LSTM model that we have developed, it is outperforming all of these process-based models in all of these cases. Yes, so one last slide. So one more thing that we were interested into, as we know in India, we have many problems. So one of the issue that we face is, I think the computer is restarting. So I'll just speak for a minute and then. So one of the issue that we have is scarcity of data. We do not have observations of a large number of catchments. So we also try to see whether this model, single model that we have developed over 55 catchments, can it be also used to make predictions at ungauged catchments? So we ran the one experiment where we removed some set of catchments from our data sets. We trained model with only those remaining 66% of catchments, and then we tested it on the remaining 33% of catchments. And we found that the model's performance was as good as it was for the catchments where it was trained. So that was the last slide that I had. And as the first speaker mentioned, that we should also know the limitations of our work. So obviously AI sounds very good. It gives you better predictions, but there are some issues that we still need to address. One major issue is with the reliability of the predictions that we get from these models. Although they work well, numbers are better, NSC is better, but still we do not have that much of confidence on machine learning models as we have on our process-based models. And the main reason is that process-based models, they rely on some physics. They know the water balance of a basin. So there's a less chance that they will go wrong. But with machine learning models, there's a greater chance that the predictions that we are getting, they might go very off. They may not follow the physics of the system. And in this direction, we are working where we are trying to develop physics-based models where we force our ML model to satisfy the physics of the system. For example, in hydrology, water balance is something which should always be satisfied. So now we are forcing our models that they should always satisfy this water balance. And that is one way of increasing the reliability of these models. So with that, I'll stop. Thank you very much. And if you have any questions, I'll be happy to take. In the meanwhile, computer is still ready.
Yeah, we can take the liberty of this thing. If you have any questions.
Yeah, sure. For that case, we compared it with HACK-RAS for the first study. No, we did not run the WIC. So the results for WIC and SWOT are coming from literature. We just compared it with similar studies in the literature.
You are claiming that DI LSTM is a very good efficiency is very good.
Yeah.
So have you tested river basin like Ganga, particular river basin? I don't want average result.
Okay.
It's result, 55 like that.
So we did not really look at one single basin, but when we were comparing these results, we compared with the literature on basin to basin basis. For example, in literature, there was no study which had all the 55 basins we had. So in one paper we found 4 basins, in another paper we found one basin. So there we compared those basin to basin, and we found that in many cases, not all, our model was outperforming them. In some cases, for example, in arid region, we found that the model is failing, and the region could be, it is not able to, the patterns are very erratic there, and the model is not able to predict there. But in other cases, like in most of the cases, it was either comparable or better. And yes.
I have some observation.
DILST. So yeah, so I think I did not have some figures, but we specifically looked at models' average performance. We looked at models' performance in predicting the peak flows, in predicting the low flows. Average, it is doing good. In peak flows, the bias that we call it, the error in estimating the peaks, it was around, I think, 15 to 20% in some cases. In some cases, it was good, depending on basin to basin. Average, it was around 15 to 20. Same was with the low flows. The model is having an error of 10 to 15%.
But
I think with low also there's a problem because many of the basins were non-perennial. There were zero stream flows. And the model sometimes could not predict zero. It gave some values. Yeah. But with high, I think 10% is still good. I would say not very bad.
supposing only that high flow, how much high flow is there, then only that intensity will be very high on the other regions.
Exactly. But the good thing is that we have only one model. We do not have, let's say, 55 models trained separately on 55 catchments. We have one model which is trained together on all the catchments. The idea is that we could also apply it for the ungauged catchments where we cannot train it. And that is something we could find that model is still doing good in ungauged catchments also. Thank you very much for your question.
Since we're talking a little bit on the integrated policy making, so I was just wondering whether the height, like the elevations are considered, and whether these kind of models could be used for a pump storage analysis. So at what point of time you're pumping water up the hill and then you're using it for electricity balance?
That is a good question, but I'm not very sure whether I should be able to answer that because that is something very different from my study domain. I do.
In the elevations.
Okay, so that elevation was basically one of the factors for predicting the flood hazard. We did not really consider pumping water and all. We looked at how the flood hazard varies with the elevation. So there might be one common thing is that the regions which are at low elevation, they will have more chances of having a flood than the regions which are on the hills. That is how we use elevation in our analysis. But pumping is, I'm not sure if I get your question for the pumping part of your question. You said
Horizon and the time slices that you are using for this model. So what you're doing is whether it's for each time slice of 1 year, say suppose 15-minute time intervals, you're finding this, or it's just one static time.
yes. So the initial model that we developed, it was static. We just developed a spatial model rather than a temporal model. And then the last.
And particularly during monsoon, and it does happen on other points of time.
Yeah. So the map was static map. It just gives us which area is more prone to flood, which has higher flood risk. But in the last slide, if you remember, I mentioned that we are trying to integrate it with the real-time information of precipitation and soil moisture. So now there we are trying to make the temporal predictions of the flood risks. So there, if we can integrate those information, now we can say that whether there's a flood risk right now or not, or in next few days or not. But the initial results that I showed, those were static. They just are useful to, let's say, disaster management authorities so that they can easily identify which are the areas more prone to floods, but they will not change temporarily.
So that's why it's like two data points which are very crucial would be the elevation and the timestamp.
Yes.
Integrated policy.
So the second part is still ongoing. We are still integrating it.
So keep that.
Yes, sure. Thank you very much for the suggestions. It's still restarting. So if you have any more questions, I'm here.
We'll take the virtual now. One speaker is there.
Okay.
We can continue discussion after.
Thank you very much.
So we have one virtual speaker. Rivas. Yeah. Okay. So now the next speaker is Dr. Monica Rivas Casaro. She is from University UK. So I think we can state request house to join. Actually, the talk is system analysis for sustainable flood management. He recognized as a leading expert in the use of UAV as a data acquisition platform to improve flood risk management in the UK and internationally. She is a senior lecturer in integrated environmental monitoring at Cranfield University. Dr. Monica is currently leading UK research and innovation and industry-funded project on system engineering solutions for robust environmental monitoring.
Excellent. Hopefully you can hear me.
Just a technical glitch over here.
Yeah.
Hopefully you can hear me and you can see the presentation.
Okay.
Working at your end, if I could have a confirmation, I would be grateful. Lovely. Can you see the slides? Slides, please.
ये कितना टाइम लगेगा?
We'll discuss later.
Yes, you can see the slides. Okay, excellent. So, thank you very much for inviting me to take part of the International Conference on Systems Analysis for Enabling Integrated Policy Making. My name is Mónica Rivas Casado, and I'm a reader in systems engineering at Cranfield University. I'm also the environment program director. And today I just wanted to have a look at a few aspects that relate to system analysis for sustainable flood management. And I would like to start the presentation just describing a few concepts of how we understand systems engineering within my
Monica, can you hold on for a second? We are having some technical glitch over here, so it will take 2 to 3 minutes time. Can you hear me? Okay.
इसके बाद फिर क्या बच्चा क्या बताऊँ? ठीक है. IMS, ISEN, and ISEN. So, welcome to Dr. Monica Rivas Casado.
Hello.
Can you hear us?
I can hear you very well. Can you hear me?
Hello, Monica.
Hello. Can you
Hello.
Yeah. So, Dr. Monica, now you can start your talk.
Okay, excellent. Can you hear me?
We can't hear. We can't hear.
Excellent. Okay. Thank you very much for.
वहाँ से audio नहीं आ रहा है.
Yeah, excellent. Okay. Namaste. Thank you very much for inviting me to this conference. I can see that the camera is moving around. Okay, perfect. And I can see my slides now. So that's fantastic. Yes, as I was saying, I'm Monica Rivas Casado, and I'm a reader in systems engineering at Cranfield University. I'm also the environment program director, and today I just wanted to talk or discuss with you some progress that we have made with regard to systems analysis for sustainable flood management. And some of the results that you're going to see here are outputs from different projects that we have had over the last 10, 15 years that now are coming together into a system of systems framework. But first of all, I wanted to just go through the concept of systems engineering as we understand it within my group. And when we talk about systems engineering, specifically environmental systems engineering, we are looking at two key principles: systems thinking and system engineering process model that come together into a framework that gives us direction, but needs to be interpreted in such a way that we can make intelligent decisions and informed decisions by project teams and their leaders, with the idea of informing management and management decisions. And that framework in itself has multiple components, which are based on the problem-solving process that you have over there. You identify a problem, you identify a solution through different modules that are described in this slide, such as system design, system architecting, concept development, and all that requires project management intrinsically to be able to get a sustainable and inherent solution or multidisciplinary solution. Not
Hello.
Yeah, Monica.
Hello, ma'am. There is audio issue at your end. Could you please mute yourself and again unmute yourself?
Unfortunately, I'm unable to unmute,
No, still
unmute
you are
myself.
not audible.
Any better?
System glitch. There is a system glitch, we can't hear.
Yeah, let me, yes, just wait.
Hello?
ऑनलाइन ज्वाइनिंग इशू वो बोल दीजिए मैं 5 मिनट में फिनिश कर लेता हूँ तब तक हाँ आप बोल दीजिए सर किसी can listen? Yeah, Dr. Monica, just now since there is some communication problem, so we are taking a physical lecture, then we'll come back to you.
Okay, no problem. I wait
Okay.
then.
I think
Once a month, yeah, that means.
It's lovely to see the audience.
today तब तक के लिए
Miss Monica, are you able to hear us? You can just say. So what I will request, we are not able to hear you. So
Okay,
can you just reconnect, log out and log in?
I will.
There may be problem at your end.
Can you hear me now by any
We are not
chance?
able to hear you. Yeah.
And now can you hear me?
Can you please kindly reconnect?
Yeah.
See, just joining. Somebody is here for physical. Yeah, take that. Take.
okay. She joined. Joined? Claudia, okay? You can just.
Yeah. Can you just unmute yourself?
I'm muted.
Oh no, it's still not able to hear you. Just what we will do, we'll take a next speaker, and by the time we'll sort out the problem.
Thank you. Hello.
We just very briefly talking about this climate modeling for extreme events. So today I'm Dr. D.R. Patnaik. So today Dr. Mahapatra sir, DG has already spoken about it. So I'll skip many parts of the thing, and already this climate modeling part I will cover. The extreme events already, as you know, because of the climate change. Yeah, climate change, it is extreme weather, it is frequency increasing. We have more frequent heavy rainfall events, heat waves, cold waves, thunderstorm, lightning, and severe cyclone. These are the common, and also leading to that multi hazards means, yeah, even the some heavy rainfall are also causing landslide, etc. So India is a land with all the type of weathers, all type of severe weather, starting from winter season, that means your cold wave, double western disturbances, to pre-monsoon season, thunderstorm, lightning, cyclonic season, then monsoon season, this is the current monsoon season, and even the post-monsoon season, October, December, severe cyclone. So it is a very unique country, all type of severe weathers are there. And these are the things, all affected area. I am not covering the thunderstorm, lightning. If you go, it is the northeastern belt is there, and heat wave, cold wave, it is more central and northwest part of India, because river basins area 40 million hectares are in over flooding area, monsoon failure, drought, and even the long dry spell. These are the all extreme event we are experiencing every year. So this is the statistics. So all type of hydrometeorological disasters are there, and this once the monsoon failure is there, you have the drought here. And even within the season also, if you are long dry spell, means if it monsoon is not there, this is agriculture risk is there. So these are the some of the examples. But yes, climate change is causing that, how the frequency of heavy rainfall is increasing. This is a known scientific factor, because the number of rainy days are less, but total amount of rainfall are not same. So that means the few days are causing more rainfall. So that means the extreme events are more. Okay, so this is also documented as per our climate study. We have the observation. So 30 years analysis also indicated many parts of the central western India, the heavy rainfall frequency, wherever the rainfall is more than 13 centimeter, very heavy rainfall, so that frequency is increasing. The number of days with heavy rainfall, very heavy rainfalls are increasing at the cost of low or moderate rainfall. Okay, so just this is the two example, 2020 and 2021, how the heavy rainfall distributed. You can see here even the September month of this is basically the withdrawal month of September. But if you see the right panel figure here, 2021, many area in September also got very heavy rainfall. So this is that means a shifting. Even the monsoon season is shifting toward the extending, so that more and more rainfall over September, October. That is also causing. Last year also we have experienced means in Uttarakhand in October month. So these are the challenging area because of the climate change, extreme weather, increasing extreme weather, timing, etc. These are the facts. Now coming to the, yes, this is observation. Another thing, heat wave. If you see, this is the area where we get the general heat wave, very severe wave, but there is increasing trend. Observation trend indicate there is increasing trend of heavy heat wave also. Tropical cyclone frequency is actually decreasing. You will be very surprised that frequency, if you say, it is decreasing total, but that means when tropical cyclone, this is intensity categorized one, depression, deep depression, cyclone, severe cyclone, very severe cyclone, very super cyclone. So as you go the intensity, it is classified in that manner. So total, if you consider, it is not increasing, but severe and very severe cyclones, that is also recent years it has indicated that it is increasing. You have seen in Arabian Sea also, Amphan cyclone, Fani cyclone, all these cyclones, so intense cyclones are there. Okay, so that is in. Then another disaster part now, which was not earlier getting attention, is the lightning. Lightning also now causing lot of death, and because of the rise in temperature, so climate change also indicating that there is increasing lightning strike. So if you these are the area, means the eastern part of and this Gangetic plain. So here more lightning deaths are occurring. Now 3,000 people are dying in lightning per year. So that is more casualty, because there are other issues also there, awareness issue also there. But so considering this, and as I mentioned in one part, the monsoon season is extending. That means monsoon now June to September was confined, but now it is even October also it is extending. That is scientifically also we have seen it. sea surface temperature, there is a continuous rise of sea surface temperature over Bay of Bengal, Arabian Sea both. At the same time, the convection also, that means more convection, more rise in temperature, that is also instability, that is also causing toward the latter part of the season, means September, October, more rainfall over the Arabian Sea area, and that Arabian Sea more convective, that is also causing the shifting of the monsoon rain toward the latter part, means late withdrawal. So that is causing the late withdrawal. And this is how the some scientific analysis, this is because of the more in convective instability, degree of convective instability increasing along with the rise of SST. So this is the we have studied some area, so that we have found out why the it is shifting. And this is a fact, observational fact also. The monsoon was withdrawing from 1st September earlier, previous 25 year if you take, but now it is delay. Its commencement also delayed, that means September 15. So that's why the season is also extending. That's why you have to focus on that part also when we are all application, even hydrological application also, because the all these things are your hydrological application, the reservoir operations are based on the rule curves. So if there is a shift of rainfall, then also that point also need to be taken care. Now coming to the service part means modeling part, means how we can in this scenario, means increasing trend of extreme, how we can provide a better service to the user community, because many sectors are affected because of this extreme increasing extreme. But if you see prioritize, you have to go by one: agriculture, water, health, energy, power sectors, and even the tourism, many plenty of sectors to all the sectors. So our focus is there. So we have to go for modeling part, that means early warning, how we can do accurate warning. So I'll give some example, very specific example. We have a supercomputer, we are our ministry, so we are with this thing 8 petaflop machines is there, so we are connected run all type of models, because numerical model based on the mathematical models are based on the hydrodynamic model. So that only can give it some sort of reliable forecast to the user community. Once the forecast is ready, so for different purpose, different weather system, we need different type of model. If I classify it into this thing, very short range to short range forecast up to 3 days, we have set of models here. You with WRF model is there, high resolution rapid refresh, radar data assimilation. Every 10 minutes radar data has to be inserted in the model. Then only you will be able to forecast for 12 hours something. Hurricane, cyclone, hurricane there. Then EWR, recently also we implemented lightning data assimilation. So these are the and another, we have also sister organization like NCMRWF. They are also having regional model. So plenty of models are there, 2 kilometer, 3 kilometer resolution, radar data assimilation. These are the area, and we will see how we are getting benefit out of this one. Then coming to the medium range, means 5 to 7 days, some system is forming depression or cyclone, how we monitor and how where it is cross, what will be the intensity, what will be the direction, where it will hit the coast, all these things that is taken care by our global model. So, and again, ensemble model, as I said, ensemble model means if you give one input, you will get one output. That means one input, one output. So that is not correct. Actually, ensemble means you have to give a set of input, then you should get a set of output. So that will take care of the uncertainty of the observation and uncertainty on the prediction. Then we have a climate forecast system, coupled model. Ocean is also taking major role for this drought and active and break cycle. So we have coupled model also. So different set of model. I'll give just some example of the event that are being predicted. So ensemble prediction, I have said, one setup, we will not go for one set of initial, we will get one forecast. We will go for a multi with slightly perturbed initial conditions. We will get a set of initial conditions, and we will go for set of forecast, so that we will have a probabilistic information, because there is uncertainty in the forecast also. So probabilistic information will be utilized. And some example. Suppose if we go for heavy rainfall, this is the left panel is your observed heavy rainfall. This is the model predicted heavy rainfall. That means model is also able to predict heavy rainfall 3 to 4 days, 5 days in advance, medium. So that disaster manager, they can take care. Even up to 5-day forecast reliability is there. That means something, means we can give warning. But as I said, one model is not sufficient. that it will be give accurate. So we are running different models. So that is multi-model ensemble. We are going for a multi-model ensemble, and if we go MME, so that is found to be the better than individual model. That's a, or whatever models are running in India as well as abroad, we have the access to real time in that data, and we are preparing the MME, and that is found to be the better than individual. So we have to improve our forecast. And you just, this is the event, as I said, monsoon season is shifting. Last year 19 October, very heavy rainfall over the Uttarakhand region, the top left panel, and this is the forecast day 1 and day 2 and day 3 based on the MME model, multi-model ensemble. So that means the model is able to capture these events 3 days in a very localized manner, I mean district level over this. So that's the capability of model, at least it can give the forecast. And this is the heat wave. We have also generating now temperature forecast. Temperature is more reliable. So the district level temperature forecast, maximum temperature forecast, then minimum temperature forecast, these are the thing model are able to capture. Then active and break cycle, as I said, couple model can give a longer period, 15-20 days, when monsoon is going to a break phase. That means model is able to predict that transition. These are the important for agriculture and water resource. So that's there. Then topical cyclones, we are not confining only one model, the multimodal track, and then the track and forecast intensity forecast also be prepared by this one. And this is the hurricane WRF model. So okay, and as DG sir was telling, yes, we have substantially improved our modeling capability of tropical cyclone in last few years. And this is the storm related storm surge. Once the cyclone is hitting a particular coast, there will be storm surge, strong wind, heavy rainfall. 3 disasters are that is called multi hazards. Means one cyclone can cause 3 disasters. And again, it will, if it is entering to the Himalayan region or a mountainous region, it will be landslide. So multi hazards. So that's a coastal, the 7,000 kilometers are vulnerable. So we are going for that multi hazards warning. Even the ocean forecast, this marine forecast, these are the area based on our model forecast. Then this is the HRR. I am giving the HRR. Means suppose 12-hour forecast we need. The radar data is more important. So we have the 2 kilometer HR, high resolution rapid refresh. Means every 10 minutes radar data assimilated, 2 kilometer resolution we will run. Then this is a case of last year WD affecting over North India. And then this is already the DG have also mentioned how the lightning forecast also is predicted using the mesoscale model. This is the recently we have introduced the EWRF. That means the electric WRF, so that it lightning data is assimilated. Observed lightning data is coming and that is assimilated. And if you see, this is observed event left. This is a global model. This is a regional model, and this is the lower. This one is your regional model EWRF with lightning data assimilation. So when we go for this one, 12-hour forecast, every 2 times we are running at it. So that will be able to tell what will be the intensity, whether lightning, then ground to lightning intensity, and which area will be lightning strike. So these are the area where we are focusing for the improvement of climate extreme weather forecasting. And this is a one example. I'm just going yesterday, because day before yesterday, we are monitoring the model. So the cloud burst of 11th August. Yesterday, there was a heavy rainfall. Today, it has come in the news, actually, Uttarakhand, Jammu region, with heavy rainfall and cloud burst. So this is, you just see how we are preparing the probability QPF, different model. And if you see here, based on the 8th August, this third day, the high probability of low rainfall, medium rainfall, heavy rainfall, very heavy rainfall over different parts of the Jammu region. So based on this one, actually, we gave this warning, and this is the cloud burst, very specialized thing. This is warning was given, that means possibility of very heavy rainfall. And today it is reported. I got it. This is the left panel. Yes, yesterday, 11th August at means early morning, 3 o'clock to 7 o'clock. So this is the left and the event. And IMD has issued a heavy rain alert in the Chamba, Kangra. Lot of modeling efforts are there at a different level with computer, supercomputer, observational improvement, assimilations, and then warning. So when we are reaching to this stage of warning, is specialized, means very extreme weather. Lot of modeling works are being done, and this is the real example. And as I said, not only the warning, we have to go for the impact phase. What will be the impact? If this rainfall is causing in this city, what are the different impacts? So we are going for impact model, and that also, and what weather will do not that what will be the weather, that is forecasting, but what weather will do, so that is also our focus. So that already explained by DGM sir, so I am not going. So summary, so this is a way extreme weather is increasing, and modeling efforts, observational efforts, and communication efforts, multi-collaborative efforts, all these things are playing a role and in enhancing the service for the sectoral applies. Thank you. I think I will not take beyond this. Thank you.
Thank you, sir. Monica, can you hear us?
I can't hear you. Can you hear
Can you
me?
say a word?
I can hear you. Can you hear me? Hello? Can you hear me? Hello? 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 Oh, you can hear me. Oh, that's lovely. Namaste. Hopefully you can see me now as well. Can you see me now as well? Oh, thank you. Unfortunately, I think I cannot hear you.
Are you able to hear me now?
I can hear you now.
Okay. So you can start your presentation. You
Lovely.
can share your
Okay.
slides.
Excellent. Thank you very much. Let me just see if I can share the screen.
Yes.
Can you see the slides now?
Yes, very much. Yes.
Fantastic, we managed. So, namaste, and thank you very much for inviting me today to the International
Namaste. Yeah, please
Conference
go ahead.
on Systems Analysis for Enabling Integrated Policy Making. I'm Dr. Mónica Rivas Casado. I'm a reader in Systems Engineering at Cranfield University, and I'm also the Environment Program Director. And today I just wanted to cover a few topics on systems analysis for sustainable flood management, which summarize some of the outputs that we have found over the last 10, 15 years within my team of research. I wanted to start the presentation by talking about the concept of systems engineering, how we see it within the group. Usually, when we talk about systems engineering, we understand that there are two main components. The first one is systems thinking, and the second one is systems engineering process model, which go hand by hand to develop a framework that give us a direction that tell us how to do things, how to interpret things. And that framework needs to be used by people that are acquainted and knowledgeable within the subject to be able to make informed flood management decisions. When we look at how the framework is set up, we look at the problem-solving process, as you can see there, which is composed of different modules. that look at solving a specific environmental challenge that we have identified at the beginning of the assessment, the analysis. And these different models comprise systems design, systems architecting, looking at the interconnections between different levels of the system and subsystems, the development of the concept in itself, and then a very strong component of project management. All this is supported by methods and tools for systems design and project management, which at the end of the day is going to give us a solution to the problem that we have introduced or we are trying to resolve. So within the concept of our research team, what we are interested in is looking at improving flood management decisions. And within that particular context, we define our environmental systems engineering challenge as the increment between the difference of the actual state that we have and the desired state that we want to go into. The actual state, and I'm just talking about our experience in England, is that we have inaccurate tools for flood extent and impact assessment. And we want to move through to a state where we are looking at accurate tools for flood extent and impact assessment. And this is going to require the development of a methodology that needs to take into account multiple components, as you can see over there, ranging from the knowledge of the team of experts, expert knowledge, experience, down to the use of standards that define professional ethics, as well as looking into behavioral psychology. And the next slides are going to summarize some of the subsystems that integrate this systems engineering solution and some of the results that we have identified for that. Our first subsystem, when we are trying to address this increment, this challenge that we have to find, is the subsystem looking at data collection. So from a management perspective, for a policy making point of view, it's very clear, it has become very clear that we need to increase the quality and quantity of input data that fits into our decisions, into our flood models, into our understanding of how flood is working. And this data collection is key because it has an impact on the estimation of flood extent and flood depth when it comes to looking at the specific cities that are at risk of flooding. On the left-hand side, you can see an example of how data input can affect the final output. This is a flood model outcome that we obtain after trying different combinations of input data. On the first top image, you can see a map of the area flooded. The river is in yellow. And that map is showing the output of the flood extent and flood depth when we are using a resolution of 1 meter, when we have collected a 1 meter resolution data set. If we use a 50-meter resolution data set, as you can see down below, you can see how the flood extent as well as flood depth is being degraded in terms of accuracy and robustness. So we are looking at defining the best way of collecting the data to have a purpose-driven data collection protocol pre, during, and post-event, and then inform management decisions based on that. Our second subsystem is looking at the data processing side of things. So within this framework of systems engineering, the second component is looking at improving or understanding how the data processing pipeline is going to affect the output of our flood management decisions. We look at the type of tools that we have used, the algorithms, how the selection of the tool is taken, the uncertainty that is associated to that particular tool. And we know by fact that that has a substantial effect on the way that we estimate our flood extent and depth. Again, if you look on the left-hand side of the screen, what you can see is the same area, the same city. This is Cockermouth in the north of England. And the flood extent and depth that has been obtained when we use a general raster digital elevation model up at the top at 30 meters resolution, straight from satellite imagery derived. And then when we use a second method, the one at the bottom, where we're using more sophisticated data processing techniques based on artificial intelligence and data fusion, And you can see how that affects the flood extent, the number of properties, houses that are being affected, as well as the estimation of the depth for that particular event. At the end of the day, that has an impact on the flood management decisions that we undertake. We move now into the third system of that systems of systems engineering framework, which is looking at technological integration. And in this particular subsystem, which is quite convoluted and complex in itself, we are looking at two different things. The first one is how the technology that we use is having an impact on the estimations of our flood predictions in terms of extent and depth. If you look on the image on the left-hand side, you can see in yellow the flood extent that corresponds to the fluvial flood extent. And then in blue, you can see the pixels that indicate that there has been specific damage within the area, within the town that we are looking at. You can see that there are pixels outside the yellow polygon. So that corresponds to surface water flooding that is not captured when we use standard technology. However, when we use drone technology, a disruptive technology, we are able to identify this additional level of impact that we have within the area. That gives us an extra level of accuracy when it comes to the detection of flood impact, flood extent, and the prediction of flood depth. That's the first component that we look at. The second component that we look at within this system is the uptake of the technology by end users, by practitioners. So there is a very social, behavioral, strong component in here, looking at the barriers of uptaking that technology and how policy and decision can help us uptake that technology as fast as possible. So quite a complex subsystem. If we have a look at the implications that that has in terms of decision making, you can see that for that area that we are working in Cockermouth in England, when we use a classic technology and we estimate the expenditure, the impact in terms of monetary terms, the total amount is 9 million pounds. However, when we look at more sophisticated technology, disruptive technology, the total impact, taking into account the pluvial affected areas, so the houses affected by surface water flooding, come up to 10 million pounds. So there's a difference of 1 million pounds, depending upon the technology that we are using for the estimation of the impact. In subsystem 4, which is the next layer of complexity that we have on these systems of systems engineering solution, we are looking at the use of outcomes. And when we think about that, we think about how we communicate this to the audience. So the people living in the houses, how they perceive the risk that they are.
Dr. Monica, just can you wrap up? Can you conclude? Yeah.
Yes, definitely. So in here, we look at the behavioral aspects of the overall research. And that informs policy from the point of view of the coordination of resources, the uptake of the property, resilience and resistant measures, and the way that we manage flood in all the different points that you can see over there. The outcome of this research and finalizing the conclusion points are that when we were affected by flooding in 2015-16, the government took a set of actions and they realized that there was a need to establish a specific grant schemes. This system of systems engineering solution that I have presented can contribute to inform the way that the grants are invested in the specific households. And also we concluded that the use of technologies such as drone and artificial intelligence, in addition to systems engineering, can substantially help improve management decisions around risk flooding. Thank you very much.
Thank you, Dr. Monica. Yeah, if there is any very specific question. in the chat box or anything? If there is no questions, let us thank the speaker. Thank you, Dr. Manoj. Yeah. So with this, we concluded the session. So this session actually we extended a little bit, started also late, but it was very good that started with Dr. M. Mohammed. They broadly talked about the MD activity already, and followed that for different distinguished talk by scientists, Dr. K.C. Gowda, Dr. And one from science. So with this thing, we concluded the session. But we like to thank each and every one of you for gracing us with your presence. So on behalf of TIFAC-IIASA, we would like to felicitate you for being our honorable speaker of the day. So first, I would like to say P.R. Patnaik sir to give the token of appreciation to K.C. Gowda sir. Please. To call Ashutosh sir. K.C. Gowda sir, the token of appreciation to Patnaik sir. Very well, sir. And we will meet after 10 minutes. The session will start. And
किससे मैं कह रही हूँ? पत्ती भाई टाइमिंग होती है। हाँ, सबकी अपनी अपनी टाइमिंग होती है। नहीं, कुछ कैमरों में नहीं होती, कुछ में कर सकते हैं। डीएसएलआर में हो जाती है, जैसे बढ़ जाती है, कुछ कैमरे हैं उसमें हो जाती है। होगा, देखना पड़ा है। अब तो वैसे भी बनती 10 मिनट की क्लिप रेंडर कर गई तो देनी हो उसने। क्या वही करेगा, कार्ड उसने लिया था तो करेंगे। घर जाके खोल देना ना इसे। हाँ, रिकॉर्डिंग में जाके ही तो देखना। ये ले, क्यों खराब हो जाएगी? कैमरे की सेटिंग है। एफएक्स का क्या मतलब है? फुल फॉर्म क्या होगा? जी मेरे मामा गए हैं। तो बिट्टू बिट्टू टेक्निकल है ना वो पीसीबी। चौसठ नहीं 128। वाह 128 काट लेके लगा के बोल जाओ। पे तो रहते हैं जैसे कल जरूरत पड़ी थी ले गए हो। घर में तो रहते हैं। और नहीं जो एक पोडियम बना लो चढ़ गए हो कभी भी चढ़ सकते।
Good afternoon, everyone. Welcome to the International System Analysis for Enabling Integrated Possibility. I, Vaibhav Singh, on behalf of TIFAC-IIASA, extend my warm welcome to all the guests and speakers. But session theme is based on resilience of climate change, agriculture and DRR. And session topic is climate observation, process and modeling. Now it's time for me to invite our keynote speaker who will formally start the session. Professor Krishna Chitra Rao is a professor at IIT Delhi. Research has focused on using climate models to understand how Earth is affected by natural as well as has been associated with IPCC work group since 2001 and concept assessment report. Sir, I would like to welcome you to the speech. Good afternoon, everybody. We are running late. What in the session is we environment. I and start this session by short. Please, okay, thank you. Welcome presentation. So, for irrigation has pronounced and India take a look at this. And we do what is right over it. And you know, this has been shown to affect the water and energy consumption. Perfect. And also in the can have okay. So we started out with looking at failure and then looking at things that find research. We see that when you add water to the land surface, as irrigation. Yeah. Other effects. Contrast with there's multiple things. Circulation. And this has been shown that in the regions where you have the highest amount of irrigation, surface temperature or has not increased and where you have more irrigation. So the student model carried out with model and to see what happens if you adding different amounts of irrigation water. You can see, I won't go into all the details, lack of time, but the maximum temperature reduces, minimum temperature. Now, move back to this coincidence areas. So, we thought that this is something that is not increasing and many here the possibility, but either as it may in the space of we are speculating in the second concept. And in 2020, there was a paper by Syria that basically showed that if you have well, greenhouse gas, aerosols, etc., what we is in the that you have only irrigation, mention an irrigation, then there's actually a decrease in liability. Of course, modeling studies can separate these things out and then also combine them. And when you combine them, then these all forcing essentially is telling us that in this over India have become less likely because of irrigation. So,
sorry, sir.
there's been other modeling studies.
Can the organizers please check the chat box?
Now, Vimal Mitra and others, they found that while temperature increases, there's and the increase leading to higher heat. But in a more in a study from group in and they think to using first model also and recommended so there's still a little bit of tension in terms of modeling study we did it right with the global model and having irrigation impact on convective rate. Happens to be in region that is all when the decay in rainfall and is the same region and land use land. This, right, but all of this is simulation wrong. You know, if our
Hello. The virtual speakers are not able to hear anything. Virtual listeners, can you please check?
I don't think anybody is listening to us or nor reading the messages, you know.
and then there's another study. With the peak is occurring. So essentially, this is a major drawback, and there's a from IIT Bombay, which actually said change irrigation from rice paddies model. So they carried out simulations and they find that it also shows that the rains are effective, but using what they think are for realistic irrigation. So there are issues that remain. This problem, oh no, adequate. People focus on the tariff and rabi season, fine, but then there's some regions that so makes it huge. And there's regional models. So what we really needed is sense and one. And that research not really. So I'm going to stop here and all right, okay.
PPT से हटा दो जो
Okay, our next Agarwal, Assistant Professor in the Department of Hydrology at IIT Roorkee. Climatology, interested in interdisciplinary research, broadly understand interactions of blood, climate patterns. If you could 10 minutes, and I'll give you a heads up at 8 minutes. Thank you very much.
Let me jump directly to science. I'm here speaking on complexity-based approaches to quantify emerging climatic pattern and extremes. The very fundamental question today I asked, why should I focus on climatic pattern? what is the need? Well, climate, we know, is divided the long-term average of the place weather. Might be persistent for some space, time, or both, known as climatic patterns. And these patterns are fundamentally linked to all the scientific inquiries. For extreme events, for example, prediction, forecasting, and that's why it's very important. Indeed, it has a analysis, for example, the figure at the bottom shows well-known climatic in the pattern in the ocean, the pattern in Indian Ocean, and so many. And a lot of studies show that when they have included these patterns in their modeling, India's prediction still has improved significantly. So a lot of people have investigated and accounted the challenges remain because of some obvious reasons. All these patterns, they vary naturally, they have intrinsic variability, and it's difficult to quantify them. In this climate change has made make it more tedious now, and intrinsically all these patterns are non-linear and carry multi-scale features. And hence, that talk is dedicated to quantify patterns using this because there exists different information at different stages. What are these information? For example, if I take the example of the state, I get different. Similarly, any process final scale is inherently a part of the process. For example, the rainfall, which is at the hourly scale, or the daily scale, currently carrying the features of the rainfall in a season. Seasonal rainfall is anyhow carrying the part of the course, for example, decadal or intra-decadal, and it is to quantify these features better understand, to have a better understanding. And what based on last am I able to do?
Hello, hello. Am I audible? Hello. Now the voice is clear. Hello. Yes. Okay. So I'm sorry for the inconvenience. We are looking. Wait. Okay. You can share your slides. I think it was mute at that time. Okay. Okay. This is it.
Okay, let me just give a quick recap. Okay, so the idea was we need to capture the spatio-temporal variability of these features. So for this, we are using complex network-based approach. Complex network has emerged as a very promising tool in the last decades. What is this? Now this is not working. Not working. No, good. So I think you clicked it somewhere. Okay, I have to go quick. So complex network is defined as a collection of the nodes interconnected by links, and these links we found based on some similarity measure. For example, if I use correlation or even synchronization, the resultant network I call the climate network. For example, here my nodes are the station, the grid stations, or maybe the observed station, and I form a climate network. And it's very active area in research. It's a powerful tool. It's basically help to reduce the complexity of your data. When you are dealing with more than billion of the nodes, it help you to reduce the complexity. Second method, very strong method, we are using the wavelet. Wavelet is a multi-resolution technique which basically help you to capture the patterns in a time domain. For example, the figure at the left-hand side, you see there's a different signal at different time domain, but the same information is very clear in the right figure. For example, there is a first signal which is only existing for the initial 1,000 steps. There is another signal which is existing for the entire time steps, and the third signal which is existing for the last 1,000 steps. So such information, if you can quantify, then we can use we can better understand this can help in the forecasting or prediction. Another important thing is wavelet can decompose the signal into various proxies. You can have the signal which represent with a different frequency, different scale. So by using this, we have proposed various methods: wavelet multi-scale event synchronization, wavelet multi-scale correlation, wavelet entropy energy measure. So this is one of the very strong, I would say, our expertise. We propose new methods. So I'm not discussing directly. I take you to the application. For example, this is a sea surface temperature for the entire globe, around 9,456 grid point, 2 degree by 2 degree. When you see these figures, it is already showing some known patterns. It is interesting. But when I decompose it and take it to the
the single scale is very interesting. But when you take it to the different scale, the question becomes very relevant, very important. For example, because we are working with to 8 months, 8 to 6 we start observing some very high linked regions in the Eastern Pacific and in the Indian Ocean, which are known to interact by atmosphere. And these regions prominent on the next scale, which is the figure 16 to 32 months, and we know it because at the scale of 2 years. And this is linked by atmosphere. One very interesting thing is there is southern ocean of which I'm not from where the connection. 4 months Eastern Pacific are heading away, but coexist with the pattern ocean pattern or the PDO, the pattern Pacific oscillation, which is in the warm phase in 70 and can be seen in hydro analysis. So it's interesting what we see at different scales. Similarly, the pattern is the subtropical of Atlantic that prominent to the next scale. And this is also one of the most of temperature to MA. And another scale at subtropical of Atlantic and subpolar of Atlantic are positive correlated, which is also a known response to MA. To make a paper is published, the note is very short. The thing is, we were able to get more information which is not available on a single scale. Let's see this figure. We also plotted the same information on a 3-dimensional plot. Fourth figure says the connections are short, which is known as the Tobler's first law of geography. Let's come to the bottom 3 figures. So the E figure says the Eastern Pacific and Indian Ocean is highly connected. Now we know it, the interaction between ENSO and the Indian Ocean dipole. The figure F is very interesting, which shows the connection going from Southern Ocean to the Eastern Pacific. This is the southern angular mode, which is the north-south movement of the westerly wind, which encircles the Antarctica. So such connections are revealed. And figure G is very interesting, which says not all the teleconnections are by atmosphere. Some connections are by the oceans as well. For example, connections are going from North Atlantic to Southern Ocean, which is the known response of or the resemble the north-south movement of the heat, which is transferred from North Atlantic, Southern Ocean to North Atlantic via AMOC. If AMOC is strong, more heat is transferred to North, means more heating in the northern part, more melting in the northern part, and more cooling in the southern part. And we have seen this a lot of snowfall in to take it to concrete, what we have done, we identified some patterns. But सारी clear जा रही है मेरे कैमरे से भी ऑडियो क्लियर आ रही है all these patterns to be in. So this figure is we published separately. We quantified the reason based on the homogeneity of extreme rainfall, topography, and so on. And this is the figure which says these patterns and so influences India, right? But which part is shown here? For example, the figure A shows ENSO, the IoT in the ocean dipole, NAO, PDO, and AMO on a different scale. So because of the less time, I skipped, but you can see in the paper. This is very interesting information which could be directly used in the forecasting model. So let me conclude the take-home message for today's slide. We have proposed we have launched basic control matters to mind.
मैं भी तो यही कह रहा हूँ ठीक है वहाँ क्या प्रॉब्लम है हो सकता है उनके इंटरनेट में issue हो।
With the material science, ecology, and economy, and we have seen such. I believe we have shown the application of sea surface temperature because the sea surface temperature as climate forcing affects weather up to a large distance. And if you understand such connections, we can better forecast and model Indian precipitation and climatic patterns. So we have unraveled the spatial diversity of Indian hydrodynamic connection, which is very important for the better weather prediction. And we have compared to other models, so multi-scale models, compared with promising. Thank you very much. I stop the
Thank you. Please for the remote participants. So we will check whether is an online speaker. Could you hear us? If you allow me, can you just unmute and we can have a short conversation before we go on to the session because there was a problem in. Is it getting better now? Yeah, is it better? Yeah, can you please speak? Apita, I think you can unmute.
Yeah, it is better now, but when you are speaking continuously one sentence, we can barely hear you.
Yeah, is that the internet problem? Because it's not improving at all.
I'm using headphone. I think this is the problem for all the online participants. So we can hear a voice, but the words are not very distinct. We cannot make out what is being said.
Could you maybe try speaking a little longer so we can check again? But the problem is for everybody, all the audience in online.
Okay. So let us try to fix it. But I think your point is when you are speaking, so what we will do, now next speaker is online, so I hope there will not be any problem. While the next talk is going,
Can't use that mic.
Hello. Yeah, this problem will.
First, can you just check? क्या प्रॉब्लम हो रहा है? कैसे साउंड जा नहीं रहा है सही? वो पुअर क्वालिटी है इन द केबल. हाँ, by the okay, I'm going to request Dr. Janani Goswami to start speaking. Hopefully, you'll be audible. Can you hear me at all?
I assume it's from Mrinalini Goswami.
I can hear you very well.
Yeah. Okay. Yeah. I'll share my presentation.
If you can make it full screen, and I again, once again, request you to.
Is it visible?
Yes, thank you. Please go ahead.
Yeah, thank you. Thank you for giving me this opportunity to present some of the findings of our research we have conducted in Center for Ecological Economics and Natural Resource, Institute for Social and Economic Change, Bangalore. Yeah, this is a little deviation from the theme because everyone is talking about climate observation. I'll be talking about observation on climate drivers. So, yeah. And yeah, initially my topic was on carbon footprint of urban household. Considering the time constraint and the theme of the session, I would like to briefly talk about the methodological perspectives of a household carbon footprint assessment. So these are some information about greenhouse gas emission. We all are aware of it, but yeah, everybody knows that India has a less per capita emission. But we are emitting, India is also emitting, but where is that carbon space used? Who can get benefited? To address this concern, we have to know the sectoral segregation of emission, who is emitting, who should cut down, who has a scope to increase the emission for the interest in the interest of development. So these are the things we need to know at a very disintegrated level. And for this, household carbon footprint assessment is very important because 70% of the greenhouse gas is contributed by households and allied activities. So yeah, everybody knows that there are a lot of carbon footprint calculators which are also available online. But why do we need a new assessment? We have come across some of the concerns with respect to those available calculators. They have included food, energy, and travel. These are the primary components all the calculators have included. But there are many consumption items, consumption heads for a household which are not considered, and the factors like geographical, ecological variation, tradition and social influence, those things are not included in such kind of calculators. And other research-based assessment are mostly input-output analysis, econometrics assessment, input-output analysis, and very few bottom-up studies are available, which are in micro scale. Again, those are very sector-specific, like for only food they are doing, for energy they are doing. So it is also important to include the geographical, cultural, economic, and social diversity of our country to be considered, and segregate the emission according to those factors. And we have also observed inconsistency in estimation, the direct and indirect emission, and inclusion of embedded emission, which part to be included, which part to be excluded, because there is overlapping of emission estimation included in production as well as in the consumption part. And there are some also contradictory results. For example, life cycle assessment of electric vehicle over fossil fuel powered vehicles, and whether plant-based or animal-based food, which one is better. Such kind of anomalies we have observed. So these are the research questions. So I don't think I'll go into the details. I'll skip this. To overcome these, some of these challenges, we wanted to develop a methodological framework for India to assess the household carbon footprint. So we went with agroclimatic zones. We selected agroclimatic zones. Then instead of taking administrative boundary, we selected landscape. Then we went for zones, rural, peri-urban, and urban zonation. Then socioeconomic strata income, occupation, etc. Then stratified random sampling of households for collecting the consumption data. This is actually an amalgamation of consumption and expenditure survey, which we designed to include all possible, all available, all existing consumption heads in any Indian households, which may vary depending on the climate, depending on the location, topography, and other cultural and social norms. So we try to include primary consumption practices, expenditure, as well as production for waste, and some of the components of agriculture in some rural households, like they cannot like some components of agriculture like kitchen garden or a few livestock which are part of the household only. So such kind of components are also included in the estimation of this carbon footprint. So further, we have done assessment to identify the determinants and what are the points we have to work on to reduce the emission. So this is the framework we and yeah. The emission factors, we have developed one very comprehensive set of emission factors, and most validated, scientifically validated and accepted factors were used in the estimation. These are the 13 locations we have covered, and in each location, rural, urban, and peri-urban zones were covered, and more than 1,900 households we have collected data. I think I'll skip this also, highlights. These are the results, some of the results I would like to show. The estimation shows that the household carbon footprint varies from 800 kg to kg carbon dioxide equivalent to 3,000. 800 is the lowest in places like Astha in Madhya Pradesh, it's a rural region, Maibang in northeastern region, and it was as high as 3,000 in Bangalore, followed by Mangalore and Noida, Varanasi. Yeah, of course, everybody knows that the contribution is mostly from the energy. At the nation level, almost 39% is contributed from energy. We try to look at the results into different way. We have taken the basic essential consumptions and we have segregated some consumptions like packaged food, frozen food, those kinds of consumptions we have segregated, and we try to see how it differs. Like for the basic essentials, it came up as 1,200 kg CO2e, and if we include the non-essential items, it goes up to 1,400. This is the average for the one Indian household. So this increase from 1,200 to 1,470, this is mostly contributed by the urban regions, mostly by the mega cities like Bangalore, Noida, that NCR region, mostly from the this is from the non-essential items we have considered. when we try to look into the income level, influence of income, we have seen that this, you can see the red line, that is the national average. All the three groups actually less than 5 lakhs are coming under the national average. And just 5 to 10 lakhs is almost falling in the national average, and 10 to 30, 10 above 10 lakhs is going above the national average. So here we can see that almost 80% population of the country, which is less than 5 lakhs, that accounts 80% population of the country is emitting less than the national average. And only the 2%, less than 2% is as high as that 3,000, more than 3,000 per capita emission. But the another point here, we should highlight that portion of the population is also ready to pay the taxes, carbon taxes. So how to reduce the emission from that section? That is another important point to consider here. So here we have done the analysis for impact of expenditure. Expenditure we have taken for proxy for income. And we could see that 1,000 rupees increase in expenditure increases 8.83 kg CO2 of household emission. And it is highest in case of travel, followed by energy and food items. We try to see the influence of other socioeconomic factors. So these are very obvious: family size, education. These things are very obvious. But what we came up with,
can you hear us?
Yes, sir.
Yeah, we need to wind up.
Yeah, I'll do it like 2 minutes.
No, in 1 minute.
In 1 minute. Okay. So knowledge, motivation, and consideration. These are like I think I'll skip this also. This because yeah. These are from the methodological perspective. These are the points we have come up with, that we need to focus on consumption-based carbon emission. That large scale of data collection should be included in the existing frameworks of data collection. For example, NSSO data collection, where more consumption parameters should be included. And we need more validation of existing emission factors, and we need a comprehensive set of validated emission factors for some items which are not included in most of the studies, but these are consumables at household levels. So we need emission factors for those things, and we need a scientific debate on the embedded emission, and rationalize the share for the producer and consumers. Which part to be included, which part to be included, that is another debate. We should have more scientific research in this regard. Thank you.
Thank you very much, Dr. Goswami. I now request the next speaker, Sri Pranav Shukla. If you can please, your talk is already on it. Sri Pranav Shukla is the Deputy Director for Flood Control Application Directorate in the Central Water Commission. His contributions in CWC includes development of 1D models for of various basins on pan-India basis. CWC Google collaboration, CWC Know Your Water app development, capacity building training as faculty for mathematical modeling.
I will.
Hello. A very good afternoon to everyone. Myself, Pranav Shukla. I am working as Deputy Director in Central Water Commission, and today I will be giving a brief insight on the current assignment of CWC and how they can be utilized to mitigate the challenge of climate change. Evidence of climate change are very well known to everyone. Here I will be limiting myself to only the extreme events and that too only on the precipitation and flooding risk. Climate change basically deteriorates hydrological cycle in a very bad manner, intensifies it. I think there is some problem with the audio. Yeah, it in turns intensified and which in turn. Hello. Yeah. It affects the rainfall cycle, like it increases the extreme rainfall events, but on the same time, it decreases the number of rainy days, which in turn put a huge stress on hydrologic structures like dams and reservoirs. They have to go for unscheduled releases, and which creates flash flooding conditions in the downstream areas. So these 5 areas have been identified as the most vulnerable areas under climate change from flooding point of view, like flood-prone areas, coastal regions, region with deficient rainfall, snow-fed and hilly areas, and the urban areas. As per the flood damage statistics prepared by CWC every year after the monsoon period, we can see that flood badly deteriorates the economy of a country in the terms of human lives, cattle lives, and the crop destroyed. Now, due to the increase in the extreme events in the past few years, we all have must heard about the major flooding catastrophes in the news, like 2018 Kerala flood, 2015 Chennai flood, and 2013 Kedarnath flood. So these are all floods are very much evident to us. So now, to mitigate the challenge of flooding, CWC basically issues 2 types of forecasts. The first one is short-range forecast up to 24 hours using gauge-to-gauge methodology. The second is 5-day advanced forecast using mathematical modeling. But the requirement of climate change is a bit more like long-range flood forecasting. So the question is, will CWC be able to incorporate this aspect in their present working environment? And the answer is yes. The reason are usually we use the flexible time series in which we can accommodate data of any length, which I will be showing in the subsequent slides. The second one is the adaptive basin models. In which the calibration parameters can be fully customizable for any type of future use. And the third important point is CWC is having a benefit of having a vast database of all the past historical data like water quality, discharge, cross-section, and all these data. So these data are also very helpful in understanding the previous response of the basin and extrapolate that for the future. Now, I will be putting some light on the flood forecasting done by CWC by modeling approach. In that, a multidisciplinary and diverse data are collected from various sources like shown in the slide, and all these data are fed into the model. In the 1D modeling approach, the basin delineation yields us the river and sub-basin information, which along with the station and dam releases and dam data, it makes a composite river network. Along with the river network, cross-section, rainfall, evaporation, all those data are fed into the mic-based system, which gives us the water level and discharge on any type of outlet, any location of outlet at the basin level. For this rainfall, along with the station rainfall, we also use the satellite or gridded rainfall like IMD, TRMM, GPM, GSMAP, all those products. The benefits of using satellite rainfall is that the timely availability, good density, and availability for the rainfall for the outer areas like Nepal, China, all those regions, which also contributes to India in the river inflow. Now, at headquarter level, we use a composite rainfall time series made by these satellite products. Like for hindcast, average of GPM and GSMAP is used, which is later corrected by IMD graded product. For the first 3 days of forecast, we use the average of WRF and GFS, and for the 4th and 5th days, we use the GFS product. Apart from these product, a new type of product is under development in our headquarter, in which we have amalgamated all the station rainfall of CWC, manual station, telemetry station, IMD stations, and also the Nepal data. And in the future, we have also planned to amalgamate the state government rainfall. So this will be a very gigantic kind of product, and it will be available on hourly basis. So right now, this data is being given to CWC field office to run their standalone model. But in future, we have also planned it to mix this in our ensemble model. Now, regarding ensemble forecast, I think ensemble data has been broadly discussed, how the rainfall data has been collected by IMD. In CWC, we are using ensemble data in 2 ways. The first one is by using it in the 15 days GeoGlows ECMWF streamflow forecast at selected reservoirs of the India, and this product is operational on our website. The second is we have recently started receiving the 10 days NCMRWF 23 membered rainfall product, and based upon that, river inflow is also being calculated. But this result is not yet operationalized because we are undergoing the process of interpretation for common stakeholder purpose. Now, in the inundation model, 2D modeling approach, event-based model have been prepared and are being run. They have to be operationalized yet. We are using various kinds of DM, all the freely available DM like 90 meter, 30 meter SRTM, and also the very high resolution DM of 1 meter procured from Survey of India and NRSC for inundation purpose. For inundation modeling, 1D, 2D coupled modeling approach has been adopted using Mike 11, Mike 21, and Mike Flood platform. So this was about the software used. Now it is time to put some light on some operational works done by CWC. This is the 5-day advisory flood forecasting website, which gives us the advance warning for 120 hours or 5 days. This website is based on Mike 11 platform, and all the Indian basins have been incorporated in these websites, like 20 river basins. And this website runs on automated manner, and this had been developed as a totally in-house project of CWC. Both inflow and water level information is available. This is a sample of hydrograph in which the red line represents the today's time. On the left side, historical rainfall and water level, and on the right side, the forecasted rainfall and water level is available. This is a sample for Tawa Dam on River Tawa for inflow, and this is a sample for Mandla station on the River Mandla. So both inflow and water level forecast are available for 5 days. A composite forecast for all the stations is also available in the tabular manner, in which the stations are automatically sorted based upon the severity of the flood. Now, some inundation modeling works, just a glimpse. This Yamuna Basin model, in which 90 meter SRTM has been used for 10 major cities among this Yamuna Basin. This is an example for Auraiya Basin inundation, sir. In the video format. For Tapi Basin, similarly, 90 meter SRTM. Map library based flood inundation atlas for Brahmaputra Basin. It is already operational on our 5-day advisory website, and it is already disseminated to the state government. Floodplain demarcation from Haridwar to Unnao on the recommendation of NGT. This work has also been completed. Kerala flood study, 2018 flood, already completed and submitted to Kerala authorities. And one major project which is undergoing in the CWC is flood prone area assessment, which will give us the scientifically actual extent of the flood prone area, which was earlier to be told as 40 million hectare by Rashtriya Baad Ayog. And for this, all the available satellite image, freely available satellite image of Landsat and Sentinel has been used to demarcate the past flooding. The data has been sent to the respected state authorities for ground truth verification, and this work is going to be completed very soon. And the last addition in our forecasting is CWC Google collaboration, in which we are giving historical data as well as the real-time forecast data to Google, and in return, Google is giving us the real-time inundation forecast using their AI and machine learning tools. So this is the example of Google Flood Alert dashboard. And on this note, I would like to conclude my presentation. Thank you, sir.
Thank you. Thank you. Thank you for an excellent talk. I now move on to a remote presenter, Ms. Indrila Ghosh. Can you please share your screen and
Sir? Yes, sir. Sir.
okay. Ms. Indrila Ghosh is presently a doctoral student at the Central University of Jharkhand. Her key areas of interest include irrigation engineering, hydrology, climate change, and GIS. Her topic is teleconnections between ENSO and summer monsoon rainfall in West Bengal, India. Ms. Ghosh, I will give you a heads up at 8 minutes so that you can
Yes, sir.
wind up. Thank you. Please
Okay, sir.
go ahead and
Is it
start.
visible, sir? Sir?
Yes, we can see you, see your presentation and hear you. Please go ahead.
Okay, thank you, sir. Okay, good afternoon, everyone. My name is Andrela Ghosh, and thank to all of you for giving me the opportunity to present before you a number of slides on teleconnections between ENSO and summer monsoon rainfall over West Bengal. The introductory part of my talk starts with what is ENSO and why is it important to study in recent years. In this slide, we have learned about ENSO. EN stands for El Nino and ESO stands for Southern Oscillation. Because ENSO phenomena mostly occurs at the southern hemisphere just right below the equator, and when we look at the term oscillation, it gives us a hint that something oscillates from one place to another or back and forth. It is an irregular periodic variation in winds and sea surface temperature over tropical Eastern Pacific Ocean. And now we should know how it all happens, and to understand how ENSO occurs, we need to break it in three phases. There's normal condition, El Nino condition, and La Nina condition. The first phase is normal condition. Actually, there is no such thing as neutral phase when it comes to any of nature's phenomena. But according to our simplicity to understand, we'll have to create a neutral state. In this neutral state, the trade winds are these winds that blow in the tropical region from eastern side to the western side. They are also known as tropical easterlies. It helps to create the equator receives great amount of sun rays, and that's what warms the Pacific Ocean. The trade wind pushes the warm ocean current towards the Asian side because trade wind blow from east to west, and that makes the Western Pacific Ocean warm. And the second phase is El Nino phase. In El Nino phase, the warm ocean current the trade winds are weak, and yes, there are a few months in a year when the trade winds are weak and the warm ocean current do not get any kind of push. So what happens in the warm ocean water at the Western Pacific slowly moves towards the central and eastern side of the Pacific Ocean. So this is where the oscillation terms come. We all know that some researchers suggested that India affected severely in El Nino years. And my research, due to my, and sometimes, and Australia or Peruvian coast also affected greatly. But in third phase, La Nina, which is similar to the neutral phase, in this phase, the trade winds is strong. Since trade winds blow from east to west, hence it pushes the warm ocean current from the eastern Pacific towards western Pacific. La Nina is more on these countries than El Nino. So El Nino is a warm ocean current and La Nina is a cold ocean current. As well as the large-scale wind patterns, this change due to. Now we should understand why is it important to study the effect of ENSO in Indian context. India is majorly dependent on summer monsoon rainfall. Due to uneven events and concentration of summer monsoon rainfall, cultivation of major kharif crops has been hampered many times. Many researchers have suggested that ENSO has impact on Indian summer monsoon rainfall. Some have suggested that heavy rain or drought has been occurred according La Nina and El Nino events. But a few researchers also have shown some contradictory results. As India has an atypical climate due to Himalaya, and Himalaya has a great effect on southwest monsoon also. So to find the proper reason behind the irregularity of monsoonal precipitation in India is not only difficult but also very experimental. It also depends upon India's physiographic variation. There is a need to find proper inference of ENSO in summer monsoon rainfall with reference to a particular physiographic approach. So so the objectives of my study were to find the relationship between Nino SST indices and summer monsoon rainfall, and the second one is to study the effect of smooth SST anomaly on summer monsoon rainfall over West Bengal. Here is my literature review according to this study, and this is my study area. It is West Bengal, which is the speciality of this study area is it has two different regions. First one is the northern one is sub-Himalayan region, consists of the lower Himalayan and foothills of Himalayan region in northern Bengal. And the other one is Gangetic Plain Basin. This is the South Bengal, southern Bengal. The region covered by sub-Himalayan region generally releases short summer followed by moderately heavy precipitation and prolonged winter. The Gangetic region generally enjoys a subtropical climate with prolonged summer followed by heavy precipitation and short, almost dry winter. Moving with the next slide with my data collection and methodology. For my study, I have collected Nino sea surface temperature indices data anomalies mainly from NOAA, National Oceanic and Atmospheric Administration, and I have taken the NCEP reanalysis dataset. This dataset is very important to study over this climate, with the present climate change scenario. There are actually six Nino SST indices: Nino 1 plus 2, Nino 3, Nino 3.4, Nino 4, ONI, and Trans Nino Index. But the commonly used indicators are ONI, Oceanic Nino Index, and Nino 3.4. And here I use three Nino indices: Oceanic Nino indices over 64 years from 1952 to 2016, Nino 3.4 and Nino 4 indices over 33 years, and smooth SST sea surface temperature anomaly for over the 64 years. And I have used the regression analysis method to collect. Here is my result. Actually, when I calculated by averaging sea surface temperatures in the region of 5 degrees south to 5 degrees north and 160 degree west to 120 degree west in each central equatorial Pacific Ocean. The ONI uses a 3-month running to be classified as a full-fledged El Nino or La Nina. The anomalies must exceed plus minus 0.5 degrees centigrade for El Nino. It's plus 0.5 degrees centigrade, more than or equal to 0.5 degrees centigrade, and for La Nina, it's less than 0.5 degrees centigrade. The anomalies are, and this is operation definition used by NOAA. Here I can see that in this from the left one, from the graph left one, I have seen in summer months in sub-Himalayan region, with the rising of average ONI indices anomaly, the rising increasing of rainfall, which contradicts the myth of less rainfall in El Nino years. But the actual relationship, the relationship, inverse relationship of in rainfall and El Nino years is followed by Gangetic region. And here is my second slide is about La Nina years. Here ONI, according to it follows the actual relationship of increasing of La Nina ONI indices with increasing of rainfall with increasing of ONI indices in La Nina years with both regions. In both regions, here is the Nino 3.4 indices. Again, on sub-Himalayan region, this index also shows direct relationship with rainfall, which contradicts the myth of less rainfall in El Nino years. But Gangetic region follows this myth. With the increase of indices, there is increase of rainfall. My next slide shows about in La Nina years. It also follows follows the inverse relationship, which contradicts the actual which contradicts many researchers' work. Like in La Nina years, there are more rainfall, but it shows the these two graphs in both regions shows the opposite map. And here is the.
Can you please wind up soon in the next minute?
Yes, sir. Yes, sir.
Thank you.
Here is the graph I have taken bar chart I have taken from IMD, and here the red one shows the rain deficit, and green, and here we can show many times in El Nino years there is rain deficit, but like many years it shows also in sub-Himalayan region in La Nina years it also shows some rain deficit years. Here is Gangetic region, and now I have concluded this with majorly Nino indices, including OA9, Nino 3.4 in El Nino years affect monsoon rainfall over sub-Himalayan region, and some Nino indices like Nino 3.4 and smooth assist anomaly in La Nina years have inverse relationships with both regions, and in normal years generally it follows the direct relationship, but smooth assist and Nino 4 in sub-Himalayan region follows the inverse relationship. Thank you, sir.
Thank you very much. We now move on to our next speaker, who's presenting remotely, Mr. Samit Kumar. Can you, are you there?
Yeah, I'm there. I'm very much there.
Yeah, please share your screen and you may get started. Mr. Samit Kumar is actively engaged in rural marketing and research with various corporates like Monsanto, Mahindra and Mahindra, and NCDEX. At present, he is working with the International Rice Research Institute as associate scientist in agribusiness and entrepreneurship development. His topic, I'll let him get started. Thank you.
Thank you. Thank you for the. Am I audible and is my slide visible?
Yes. Yes, we can see your slides and hear you. I'll give you a warning at about 8 minutes. Thank you.
Thank you so much. Thank you so much. Thank you for this opportunity and thank you for the sweet introduction. I'll straight away go to my topic. Friends, as you know that agriculture is both a cause and victim of climate change. So my presentation will mostly accentuate on the research done on climate smart agriculture for enhancing livelihood resilience and women entrepreneurship in Odisha. And with me, Dr. Sapna Arora is there, who is my mentor and guide for this research. Now, friends, before we move on to the main part of the presentation, I would like to draw your attention towards one of the most important dimension that has been negatively impacted in India, and it has also got a very close link with the climate change, and that is the decreasing operational and operated land holdings. Now, this data I have picked from the agricultural census of 2015-16. If you look at the histogram, the first one, you will see that the average operational land holding has been on a decreasing trend across last 50 years. Now, as we speak, it is close to 1.08 hectares. And what does it mean actually? We need to look at it from a smallholder farmer point of view. If a farmer is holding 1 hectare of land, it is very, very difficult for him or her to generate the marketable surplus. Not only that, whatever the government schemes are there, whether it is the climate change schemes or the normal schemes or the technology per se or the advisory services, it becomes extremely, extremely difficult for them to percolate to the last mile farming community. So if I want to put a number to this operational land holding, it is close to 150 million numbers. I mean, in India, if you look at 150 million operational land holdings are there, out of which almost 126 million is small and marginal, and which forms close to around 74 billion cropping or operated hectarage. Now, when we talk about small and marginal farmers, this is the hectares that we are talking about, 74 million, which forms 47% of the crop area. Now, with respect, why I'm taking paddy into consideration is because in Odisha, almost 78% agriculture is paddy only, and paddy is grown in almost all the seasons. So if you look at paddy in India, it is almost 44.3 million hectares that is grown, and 80% of the paddy is grown by small and marginal farmers. This is what are the different climate impacts on agriculture. I'm sure people have talked about this a lot, but I'll just focus on one of the things that the World Bank report, which says that we need 70% more food production by 2050 to feed an estimated 9 billion population by then. So agriculture has to take the center stage, and with the climate change coming in, it will become more and more challenging for everyone to participate in this. The carbon dioxide concentration has gone up by 412 ppm, and almost zero, as per IMD, average temperature has risen by 0.6 degrees Celsius. What does this mean is actually the different biotic stresses that we talk about, like pests and diseases. These are going to increase. The pests which were not the key pests earlier are becoming the key pests now, which is obviously decreasing the productivity as well as well-being of farmers, and specifically the smallholder farmers. The greenhouse gas emission has increased by 80%. And that's why I was talking about paddy, because 33 lakh metric tons of methane is released by paddy. But we cannot negate paddy at all, because it is, as I said, it is grown in almost 78% of area when it comes to Odisha. So estimate also suggests that 75 to 80% of nitrous oxide emission comes from chemical fertilizers. So we have talked a lot about these stubbles. So if you look at in India, 600 metric tons of stubbles are generated, out of which 16% is burnt, and out of this 16%, 40% of stubbles that is burnt is paddy. Now 1 ton of paddy, when it is burnt, it creates almost 1.5 tons of carbon dioxide, 2 kgs of sulfur dioxide, and 3 kg of particulate matter. I mean, the shoutline of this slide is that agriculture as such, when it comes to climate change, is more vulnerable. I'll go to the next slide. Yeah, so the assessment of vulnerability to climate change. Now, agricultural product, this slide is, I'll just brief on this slide, that agricultural productivity is sensitive to 2 broad classes of climate induced effects. There's the direct effect and the indirect effect. And third is, of course, the socioeconomic effects that we talk about. When you talk about the direct effects, it emanates from the changes in temperature, pressure, or carbon dioxide concentrations. Whereas the indirect effect is mostly through the changes in soil moisture and the distribution and frequency, infestation of pests and diseases, cyclones and heat waves. So when we talk about the assessment of vulnerability in agriculture, we need to look at it from the environment point of view, from the biophysical point of view, and from the socio-economic point of view. Now, why Odisha is considered as a hot spot of climate change? Now, out of the 105 years, 95 years, it has been under a disaster affected. It has been declared as disaster affected. Floods, drought, cyclone, the abiotic stresses, you name it, and the Odisha has it, whether it is floods, drought, cyclone, salinity, seawater rising, or heat waves. But the important thing is that in Odisha, 75% of population is dependent on agriculture. And as I already, I just reiterate, 78% of cultivation is rice. 70% of this cultivated area is drought prone. So the food security as such, the threat of food security is looming large. And to make things worse, the average land holding in Odisha is close to only less than a hectare, just 0.95 hectares, and 93% of farmers are small and marginal. Also, the seed accessibility, when the farmers go for farming, the seed accessibility, affordability is a big issue. Also, the varietal replacement rate and the seed replacement are very, very minimal. So that again impacts, along with the climate change, these factors also impact the productivity and returns for the farmers. Now, if you look at the rising sea level, the gushing seawater, it not only decreases the productivity, but it also makes the soil infertile. So one of the estimates says that with the rise in 1 meter of sea level, almost 170,000 hectares get submerged. The groundwater depletion is close to, in 24 districts out of 30 districts. And there has been alteration in the flowering time, leading to poor yields, poor quality of the end produce, and thereby leading to negative returns or the distress sale for the farmers as well. Summers have become longer and winters warmer as the seasonal cycle has been changing. Earlier we talked about 4 seasons in Odisha, but now it's just 2 seasons that we talk about, just Kharif and Rabi, that's it. So the farmers are sometimes not able to take even 2 crops in a year. When we talk about
what?
Yeah.
It's if you can wind up in the next minute or so, it'd be. Thank you.
Okay, sure. So now evidence suggests that the women are more meant to climate change in terms of securing food, feed, and fuel and water. So this study actually encompasses the role of women and how the resilience can be built to vis-a-vis the climate change. So this is all about how what is the kind of participation of women in agriculture is like. The role is limited to nursery raising, transplanting, and harvesting, and their poor accessibility to productive assets, resources, credits, markets, and inputs. So these are some of the livelihood resilience practices that have been taken up in Odisha, and that has found promise in combating the climate change. The crop intensification and diversification in Odisha, almost 1.1 million hectares of rice fallow area is available. And if it can be brought under the second crop cultivation, then definitely it can have a suitable effect on the climate change, improving the varietal replacement rate and the seed replacement rate, different stress-tolerant varieties that can be grown, gender-responsive mechanization can be taken up, agroecological measures in terms of biofertilizer and biopesticides can be taken up. Then there is carbon farming, which helps in generation of carbon credits and all through a participatory approach. And food and dietary diversity has taken the central stage here, where with vis-a-vis the crop diversification, the different crop management practices that can have a positive impact on the climate change. The ICT, the role of ICT tools, we have seen that how the GIS drones and digital shared services have been able to carry out the optimized mechanization, crop management, or residue management practices here. I'll talk about the women entrepreneurship part. This is a model that has, that has become favorable in Odisha in terms of forming the collectives, because there are a lot of self-help groups in Odisha. If they can form a farmer collectives and can build up on that with respect to commercializing the different things, then they are in a better position to combat the climate change. So in the end, this is my concluding slide. The sustainability, as I see it, is more of a increase in productivity, increase in marketability, and increase in profitability. Until as all these three things are taken care of, vis-a-vis the climate change, then the smallholder farmers cannot be more resilient. They will be more vulnerable to all these things. The upstream, midstream, downstream activities, all this echoes with whatever I have already explained. So I'm not going to deep down into it further. Thank you so much for your patience. Thank you.
Thank you. Thank you, Mr. Sumit Kumar. I will now request another remote speaker, Professor Arpita Mondal. If you could please share your screen and start your presentation. Okay. Professor Arpita Mondal is an assistant professor at IIT Bombay. Her areas of expertise include detection and attribution of hydroclimatic change, spatiotemporal modeling of extremes, hydrologic statistics, uncertainty modeling, climate change, statistical downscaling, frequency analysis of floods and droughts, including regionalization, risk assessment under non-stationarity, and urban flooding. Professor Mondal, please. Yeah, can you speak? I hope we can hear you.
Can you hear me?
Yes, we can. Please go ahead.
And you
And
can
I'll
see.
give you. Yeah, we can see your slides.
Okay. Are they in full screen mode? Can you see them in full screen mode?
Yes, but there's a gray box. I think you need to minimize that window.
How about now?
Okay, it's smaller in size, but please go ahead.
How about now?
Yeah, it's out of the way.
Okay. All right. So a very good afternoon to everyone, and thank you for really patiently waiting in the session. And I will I will briefly present my talk here. So I am actually an associate professor in the Department of Civil Engineering, but I'm also associated with the interdisciplinary program in climate studies at IIT Bombay. And in this study, the slides are not moving. Well, do you see the next slide, which is called hydroclimatic extremes in
Yes.
India? Okay.
Yes.
Right. Yeah. So typically, I usually begin with the question to my audience, asking them to recollect any extreme event that they have seen, and typically also the response is that no person nowhere in this world would have not seen any extreme events. So India is also no stranger to extreme events such as heat waves, floods, and droughts. And we all know that these days, because of climate change, these extreme events are altering in terms of their frequency, their intensities, and as well as the durations. So let's first understand how heat waves are associated with climate change. So with global warming, we have the means of the temperature increasing. So as a result, the whole distribution, so the distribution of temperature changes from the dotted one to the solid one. And therefore, what used to be your upper tail, so all these regions which used to be in the upper tail are becoming more and more likely. So that's how heat waves are expected to change with global warming, with changes in mean temperature. We are also expected to experience more heavy precipitation because a warmer atmosphere can actually hold more moisture and keep absorbing the moisture, and like a sponge, it eventually dumps the entire rain. So extreme rainfall is expected to get more intense and more frequent, and as a result, we have more floods. Now, increase in floods does not necessarily mean that the other end of the extreme will not be affected. In fact, we see that because we have higher temperatures, we now have more evapotranspiration, decreasing the water availability. So precipitation minus evapotranspiration, in some sense, in a loose sense, will give us water availability, and that reduces because you have more evapotranspiration. So on the other hand, we are also are also more likely to experience more droughts. So this now let us see how these extreme events have been changing in India historically and more so in the recent past. So the IPCC's reports tell us that for the South Asian regions, when it comes to hot extremes, there is an increase. And the three dots that you see here signify our confidence in the conclusions that these are linked with climate change. And that's what we have been seeing in other in literature, in studies, which show that if you have the chances, the frequency of having concurrent day and nighttime heat waves are shown to increase, as you can see in these two images. The trends in daily maximum temperature have also been increasing, as we see here in this panel. The distributions indeed have been shifting from the non-global warming period, the blue one, to the red one. And we also have the trends in frequency and duration of heat waves increasing in India. Now, when it comes to heavy rainfall, we still see an increase. So the green signifies increase. The confidence is a little lesser. But we do see an increase in the heavy precipitation events in India. And that's what we have also seen in literature. We see that in the core monsoon region, in the central part of India, frequency of extreme events have been increasing, and overall the total volume of rainfall which dumps as an extreme rainfall is also increasing. Now, there is a slight disagreement in literature as to whether this increase can be attributed to increasing spatial variability. But overall, I think there is an agreement that heavy rainfall events have been increasing, at least in some parts of India. Now, when it comes to drought, we see that the color of the South Asian region in the IPCC's report is white, which means that there is very low agreement in the type of change. But we do see literature which report that when it comes to concurrent heat waves and droughts, which can be classified as a compound event, the trends are increasing. So if we look at this figure, the 95th percentile heat waves, which are concurrent with a drought, then a lot of regions are marked in red because the frequencies of such kind of events have been increasing. And in our work, we also try to define characteristics of droughts such as severity and duration. I'm afraid it should have been duration. So those two also, we see that the trends are increasing. And the number of drought events in the recent years, 1971 to 2004, have been more as compared to the past, 1936 to 1970. So with this, we try to investigate, what role climate change plays and how we can decipher that role. And for this, to understand, let us say you have an extreme event happening, let us say a drought of 2015, or the heat wave which happened this year, 2022 was a very severe heat wave for several parts over India. So we try to understand whether climate change has played any role in that, and how we typically address this problem is we calculate two probabilities. Very quickly, an analogy we can take is from the field of epidemiology, where we cannot say for certain whether a particular person dying of lung cancer is dying because of smoking. But we know that in a statistical sense, smoking increases the chances of having lung cancer. So here also we address the question in a statistical sense, and we calculate two probabilities, P1 and P0, the probability of the event happening in a world with climate change vis-a-vis the probability of the event happening in a world without climate change. And then we look at what is the change in these two probabilities, how many more times this event has become more likely. So attribution of extreme events have been attempted in literature for heat waves, where we have a larger confidence. The blue and the red basically show the probabilities in a world without and with climate change respectively. And what we see is that for heat waves, again, we have an unequivocal attribution is possible, whereas when it comes to heavy rainfall or floods, so here we see results for the Chennai event, and here for the Uttarakhand event of 2013, the Chennai event of 2015, we see that unequivocal attribution to climate change is not possible for heavy rainfall events. Now, what we decided to work on was the 2015 Marathwada drought, which was so severe that, this image is from a region called Latur, where the region was suffering from such a large water deficit that a railway wagon full of drinking water had to come to the place for the people to survive. And here we look, when we rank these events, we see that in terms of cumulative rainfall and temperature, this event is on the higher side. It lies within the top 10% of all the events. And we also looked at, the concurrent deficit in rainfall coinciding with a high temperature. And the idea there is that their concurrence will eventually lead to a lack of soil moisture, leading on to, again, loss of water availability. So what we see here is when we plot the temperature and rainfall anomalies, the 2015 event lies in the third quadrant and at a very high location, meaning that it had simultaneously high temperature and low rainfall. So then we adopted this probabilistic event attribution to a multivariate context, where we look at a joint CDF. So instead of looking at the individual distribution and how they're shifting, we looked at contours, which basically plots both temperature and rainfall. And in those contour plots, we try to see what is those probabilities P1 and P0 respectively. And what we see is, yes.
Could you please wind up in the next minute or so?
Yes. So what we see for the 2015 event is that based on observations as well as model simulations, simply the rainfall deficit alone was not rare, but when we consider a hot dry event rainfall deficit along with high temperature, we see that what used to be a 1 in 500 year event has now, because of climate change, become a 1 in 100 year event. So the event has been made 5 times more likely because of climate change. Now, what are some of the challenges and path ahead? Of course, good quality and quantity of observational data. Our speakers spoke about this role of confounding factors. Professor Krishna spoke elaborately about the role of irrigation, but there is also aerosols, which are believed to be cooling because of their reflecting nature. But in India, we also have a lot of absorbing aerosols because of biomass burning, and which can actually lead to warming instead of cooling. So these confounding factors and their roles need to be properly understood. There's also non-stationarity, which means that whatever relationship we have between the variables may not likely hold true in an altered climate of future. And eventually, these attribution results need to be linked with impact, such as crop loss or mortality, and how they can be linked with vulnerability. So these are some of the areas that need our attention. Thank you very much.
Thank you very much for a nice talk, Professor Mandal. We now come to the last talk of the session. I invite Dr. Gyanendranath Mohapatra to make an in-person talk. So please get started. Dr. Mohapatra is currently working as a principal scientist at CSIR Fourth Paradigm Institute in Bangalore. His research domain is mainly on mesoscale modeling of the hydrometeorological disasters like extreme rainfall events, tropical cyclone, urban flood, etc. Presently, he's working on a CSIR project on urban flooding. I will give you.
Hello, good afternoon to everybody. So I was listening since last 1.5 days regarding extreme events and its impact on climate change, and what is the policymaker they are going to do whenever they will accumulate all this information, that what is happening at what level and what extent. That is very important thing. So I'll skip a lot of my slides because it is not necessary but to give the information. Now Google information is available everywhere. Whatever changes is going on, rainfall increasing, decreasing, what is its impact on climate change, which area is increasing, why increasing, and all those papers people are writing very sincerely, and I found these papers are very useful also for a researcher like us. And here I'll go through the diagnosis part of extreme rainfall events in urban areas. Why it is happening, what are the reasons, and what extent we can support our model, mesoscale model, which is driving these extreme rainfall events. So first, I think 2 slides. These are the challenges. Configuration and validation. How will configure it? What are the domain size and role of a parameterization scheme in the mesoscale model? It's a very, very challenging, I'm telling you. Because whenever you are configuring a larger area in a domain size, it has some changes. And you have to fix the domain size whenever you are looking at the intensity. If you are forecasting it in a forecasting mode, then you may not be knowing what will be the intensity. But from the hindcast mode, what are the results you have got it, you can configure it. And next, the parameterization scheme. It's a very, very challenging optimization technique. Parameterization scheme in the sense cumulus, physics, and land surface model, soil moisture, and external satellite data, observed data. These are the components we are trying to put in the data assimilation system. Normal running this dynamic model, it has a lot of error. I can tell you up to 30 to 40% error it will show. People will claim many things, but actually it is not feasible to directly forecast getting the forecast data from the musical model and putting it in the dissemination decision support system. It is not the right thing. First, you have to go for all these, I can say, traditional setup of the model. You have to incorporate data simulation system with your observed data from it may be from TRG, or you may be from the observed some various stations. Try to assimilate it in a proper boundary condition. All these data models are running depending upon the external boundary condition of the global model. So actually in the global model, what happened? There are some errors. Whenever we are downscaling it to the local model, then this error will be little bit escalated. And again, whenever we are not fixing the boundary condition, planetary boundary layer, and the initial condition, there is always a initial value problem we are trying to fix in the model. So what happened? This error can be escalated in your forecast system, and it is very surprising. After 72 hours, giving the accurate forecast, it is really a challenge. You can maximum 24-48 hours you can do forecast, and that is the possibility of accuracy is around 70%, I can say. But beyond that, there is some issue, we have to sort it out. This is the All India rainfall. I have taken 117 years data. So you can find this is a normal pattern, but central India is a very deficit area, and we found that in the other part of this, like month of July and August, there is some high rainfall in that east and west part of the India, and this is the normal tradition, and it is published in the I can say the theoretical and applied climatology. And this is the interesting average Indian rainfall. Taking any model is, I think, not worth. What we have to do, we have to segregate. And model, whenever we are fixing our resolution, running at 1 kilometer resolution whole India, it is a challenging task. Our HPC won't support it. I don't know. In 2 petaflop we tried, but it is very difficult, downscaling it. So what we'll do, we have to segregate in the different meteorological station. We'll try to divide it, and we'll run sector-wise, we'll see the results. And I found some interesting result. There are some temporal variation in rainfall within spatial group based on the cluster analysis and average monthly rainfall system. So some dry area, wet area, we have to identify through this meteorological subdivision. Then we can say in this division, these are the changes happening, and we have to take care of this thing. And whenever you are fixing also model, land surface pattern, whenever you are giving assimilation system, you have to give very carefully what are the LAI, soil moisture pattern, what are the different parameterization scheme when we are putting in the physics model, then you have to take care of all these things. And this is a very interesting thing. In the urban extreme rainfall events, what are the parameters that we have to put? How to fix that it is the extreme rainfall events? It depends upon the time to time and space to space. We cannot say Jammu Kashmir, whatever rainfall is there, we cannot say that is in Bangalore, that will be called as extreme rainfall events. So you have to average it, take 95% of that average and fix it as extreme rainfall events, and try to model it. I have taken around 30 cases with a different parameterization scheme, and I have done hit and trial method with a different parameterization scheme. I found some of the specific physics scheme and cumulus scheme is giving some good result. Good result. I am not taking the responsibility of telling that it is a very accurate result, but good result it is showing. So whenever you are trying to run any urban extreme rainfall events, you have to be careful taking this physical parameterization scheme and cumulus scheme. And second thing, there are some other factors like urban heat island. As Achyut Rao sir told that these are the ET, evapotranspiration, and other parties like latent heat, and the topography of the area, and how much heat radiation you are getting, and what are all these things, buildings, height, and radiation factor, all these are coming under one umbrella. And each sector, I can say each variable has its role whenever you are trying to give an initial boundary condition. So I am basically telling to the young modelers, they have to be very careful whenever running all these things with all these available data or satellite data, and you can modulate according to your requirement. So this is a initial boundary problem I can show in this paper, that is map. All the models take some spin-up times. So whenever you are deciding your initial condition, be careful about your spin-up times. So 0.6 hour, I found 30 cases. I have taken 30 cases of different intensity and duration. It is a very good thing that 0.6 hour, whenever particularly I am taking, it is showing good result. And this is some of the extreme two events I have compared it. And that is also same thing in the model. And this is a forecasting we have done at 2 kilometer resolution. Sorry, this sub-kilometer, 600 meter over Karnataka area. So we found more or less that confidence level till now, it is not coming to go to the public platform and tell that we have done this thing and this is our model, 70% accuracy is there, you can blindly follow us. That confidence till not we have built in our modeling platform. And next thing I can go, these are the Bangalore's, not necessary to show. Yeah. And finally, I'm trying running some very, I think localized area I'm coming. I'm trying to model some Bangalore area, that is KC Valley. I'm trying to see how much there is a runoff and hydrography showing how much spread in the flood area. That SWMM I have tried. And I'm trying in a good result. There are some areas it is showing that model is performing well, and some area it is not good. So these are all. And this is the soil moisture pattern I have tried. And future roadmap, 4-5 points I will tell here. First thing is, whenever you are deciding, be careful about the domain size and parameterization scheme. Second thing, data simulation is the best way nowadays to do the modeling. Third thing, whenever you are taking the data of a specific data like land surface model and soil moisture model and canopy model. Canopy model is a very good thing that you can incorporate with the model, and that can show a good result. So all these things should be take care whenever you are going to do the measure scale modeling system. Thank you. Thank you very much.
Thank you very much, Dr. Mohapatra. With this, we have come to the end of the session. Since we have spilled over in time so much, I apologize to everybody for not having time for a Q&A or a discussion. I hand it back to you. Thank you.
Okay, thank you, sir. As we have reached to end of the session, we would like to thank each one of you for gracing us with your presence. On behalf of TIFAC and ISA, we would like to felicitate you for being Honorable Speaker of the Day, sir. Okay, so I would request Krishna Achyuta Rao, sir, to give everyone a token of appreciation. So I would like to call Pranav Shukla, sir. Now I would like to call Gyanin Nath Mohapatra, sir. Now Ankit Agrawal. Now I would request Gyanin sir to give token of appreciation to Krishna sir. Okay. Thank you very much. We can have lunch.
Hello, can you hear?
Yes.
Okay, good, good. So we will start this session after plenary will end, right?
Hello. When we are starting?
Sorry?
When we are starting the session?
I don't know. I'm waiting for
I see.
information.
Okay, okay.
Yes.
Okay,
Me too.
okay.
I thought we were starting before this.
Yeah.
Yes, yes, yes.
Yeah.
But still the plenary session has been continued, so I think we need to wait.
I see.
Okay.
Starting in 5. Someone just put in chat. Starting in 5 minutes.
Okay. Let's wait.
How much time you are going to give for presentation or presentation?
Around 8 to 9 minutes because time is very much
I see.
tight.
I see.
Yeah.
Similar.
Yeah.
And is there any time for question answers?
Sorry?
Is there any time for question answers or is just?
Yes, I'm going to take around 1 to 2 minutes.
Okay,
Very much
okay.
short question and answers.
Okay, okay.
But it depends. Yeah.
Okay. Good, good. Because time is at premium, so.
Mm.
Hello. Hello.
Hello. Hello.
Am I
Yes,
audible?
yes, we can hear clearly.
Okay. Okay, sir. Sir, we are going to start the session in 4 to 5 minutes.
Okay.
Sorry for the delay.
Okay. So please let us know when it will start.
Yes, sir. Yes, sir.
Okay, thank you.
Okay. We have one. Ma'am, do you have session in here? Yeah. Yeah. Anjana was? Yes. Yeah, okay. Okay, ma'am. Ma'am, can you share your PPT?
Yes.
Okay. 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 Not an issue.
So I can control my slide, right? Because
Just
I
you
have
can.
animation.
Yeah, ma'am.
Great.
From this, I'm giving you. So let's start the session. Yeah. Hello. Good afternoon, everyone. Welcome to International Conference on System Analysis for Enabling Integrated Policymaking. I, Vaibhav Singh, on behalf of TIFAC and IIASA, extend my warm welcome to all the guests and speakers. Today's session, our theme is based on sustainable energy transition in Asian countries, and our session topic is transforming to a net zero emission energy system, opportunities and challenge. So now it's time for me to invite our keynote speaker who will formally start the session, Dr. Tutsaya Hanuka, is currently head of the Global Sustainability Integrated Assessment Section in the Social System Division at National Institute of Environmental Studies, Japan. Dr. Hanuka has also been a member of Asia Pacific Integrated Assessment Modeling Project. Dr. Hanuka current area of interest includes the development of integrated assessment model and research on environmental policies for low carbon society. Dr. Hanuka, over to you.
Okay, thank you very much. Okay, thank you very much for attending this session 9. This is the last session on day 3. So there are 8 speakers, including myself, within 90 minutes. So I would like to ask that all topics are very much interesting, but the time is very much limited. So I would like to ask each speaker to keep your time around the 8 to 9 minutes, and I will take a short question, Q&A, around 1 to 2 minutes. So once again, we are way behind the schedule. So
Sir, sorry for bothering you. We have to finish it by 4:15.
Okay, so we need to move quick. Okay, now I will share my screen. Wait a moment. And also, wait a moment, I will turn off my camera. Can you see my screen?
Yes, we can see.
Okay, good. Okay, thank you very much. So today I'm going to talk about the carbon neutrality pathways in Asia and the importance of the co-benefit and the trade-off effect. Okay, next slide. Wait, why it doesn't move? Once again, wait a moment. Okay, yes. So this slide shows the diagram about the relations between the mitigation options and SDGs reported in the IPCC AL6. The main message is that the GHG mitigation options have synergies with many SDGs, but at the same time, some options can also have trade-offs. So this is very good looking diagram. However, it is unclear how the level of confidence of synergies and trade-offs were evaluated quantitatively. So it is important to develop and utilize integrated assessment model to quantify, quantitatively evaluate the level of synergies and trade-offs. Next. So when we evaluate effect of co-benefit, coal combustion is one of key discussion points. So coal combustion is a major source of CO2 emission. This is the reason why coal phase down was mentioned at COP26 Glasgow Climate Pact. However, I would like to highlight that the coal combustion is also the major source of air pollutants, especially PM2.5 and SO2, and also short-lived climate forces, especially black carbon, and also mercury. And in the process of coal mining, methane is emitted, and methane is the short-lived climate forces. And in Asia, especially, the share of coal power is very, very large, around 60% of electricity generation in 2015. Therefore, the coal phase down is very important from the viewpoint of environmental conservation, and also important to consider co-benefit effects in reducing SLCFs and air pollutants and mercury in Asia. And this figure shows the current situation of anthropogenic emissions of CO2 and non-CO2. Asia accounts for a large proportion of the air pollutants, such as black carbon, PM2.5, and SO2. And the NOx, CO and NMVOC, those are the precursors of the tropospheric ozone. And methane and black carbon and the tropospheric ozones are short-lived climate forces. Yes, and Asia accounts for a large proportion. Then coal combustion is the major source of those gases. And also, when we see the anthropogenic mercury emissions inventory in 2015, again, Asia accounts for a large proportion. around 60% of global mercury emissions. And coal combustion is the one major source of mercury emissions in Asia. Therefore, it is very important to reduce coal consumption in Asia, not only to reduce CO2 emissions, but also to reduce air pollutants and SCFs and mercury emissions. And at our institute, we focus in Asia especially. And we have been developing Asia-Pacific Integrated Assessment Model, and we have international collaborations among Asian countries. By using the AIM models, we discuss mitigation targets and roadmaps to achieve 1.5 and 2 degree target in Asia countries. And we developed mitigation models, impact and adaptation models. But due to time limitation, I will briefly explain only one mitigation model named the AIM End-Use Global Model. This is bottom-up type optimization model with detailed technology selection framework. This model covers global regions and the major sectors. Then we utilize this AIM End-Use Global Model to analyze and discuss co-benefit and the trade-offs by considering the complex combinations of mitigation measures. Then from now, I will show you some example figures about co-benefit analysis. And this figure shows the co-benefit analysis when achieving the global 2 degree target. So to achieve the global 2 degree target, we need to cut global CO2 emissions by half compared to 2010 level. And it means that the CO2 emissions should be also reduced more than half in Asia. And if we see country by country mitigation options, mitigation potentials and sector by sector, the role of the power sector is important to reduce CO2 emissions largely. But at the same time, if we see co-benefit effects in reducing air pollutants and mercury, yes, we can also see large co-benefit reduction effects in power sector. This is mainly because of the effect of coal phase down and also efficiency improvement. But in order to achieve 1.5 degree target, the coal phase down is a necessary direction from the viewpoint of environmental conservation, and energy mix in power sector should be shifted to the carbon neutral in Asia. For example, more coal phase down, the more energy shift to renewable energies, and 100% deployment of CCS for fuel power plant, and also biomass power plant with CCS. However, even if we understand the coal phase down is very necessary direction, there are some barriers and issues from the viewpoint of economic development in reality. For example, there are economic capacity to promote more coal phase down, energy security and energy portfolio to provide affordable electricity to the demand side, and stable electricity and energy access to solve energy poverty. So in Asian developing countries, we face with those issues when discussing coal phase down. Then this is last slide. I would like to mention one more point about the limitation of co-benefit effects when comparing the 2 degree target and 1 degree target. There is significant difference between 2 degree target and 1.5 degree target in terms of CO2 reduction. However, the difference is very much small in terms of the co-benefit effect in reducing non-CO2. For example, about the black carbon emission under the 1.3 degree target, co-benefit effects are almost the same as a 2 degree target. So in order to reduce more black carbon emission drastically, so it is necessary to introduce a further electrification in the residential sector and the transport sector, and also further removable measures in the power sector and industry sectors are required. And if, for another example, as for SO2, under the 1.5 degree target, we can see that those co-benefit effects are large than those under the 2-degree target. However, in order to reduce more SO2 emissions drastically, further renewable energies in power and industry, and also the further removal measures in the power and industry sectors are required. Okay, those are the summary of my presentation, but due to to save the time, I would like to move on to the Q&A. Thank you very much for your attention. So I cannot see the hand. Okay, I will stop my sharing. Do you have any questions or clarifications, short questions or clarifications to my presentation?
Yeah, I have one, one basically, whatever you call it, question or clarification.
Okay.
This is in context of poor Southeastern regions. Coal phase down, apart from various other regions. One region is coal mining is concentrated, for example, in India, in the poorer regions. The poverty and coal mines are concentrated in one region in India. So when you do coal phase down, you require massive compensation, and also you will have problem in terms of migration of population. So what is your view on that?
Okay, thank you very much. This is very difficult the question to answer for me. Yes, I understand that. So we need to carefully consider the local situation when we discuss a coal phase down. So coal phase down is the ideal direction from the viewpoint of the CO2 reduction and also air pollutant reductions. But we also need to take into account the local situation, so which you mentioned. I really understand. So we need to discuss how to shift the situation very much carefully with the local partners. Yes.
Thank you.
Thank you. Yeah, thank you very much. I will take only one more question. Okay. Yes, I saw your hand. The Bhattacharya. Can you please? Okay.
Yeah, good afternoon, Anauka Sensei. So my name is Aninda Bhattacharya, and I earlier I worked with IGS also for 8 years, and I met you several times. I don't know whether you remember me. But I have a question regarding your scenario. Actually, we do a lot of work in India also regarding the low carbon transition, including the coal phase down, what you are also showing through a model. So here we are using the message IX model. But I have a question because what I saw from your presentation that you have incorporated a lot of CCS. Now, question is that, the CCS with coal and CCS with biomass, how feasible that is in the Asian context, that is a big thing because none of the countries in Asia are really looking forward for CCS. So in the context of net zero, coal plays a very major role. And so how in your model you are considering, so is it only on CCS or you have any other scenario where without CCS also you can bring down the emissions? I'd like to know from this.
Okay, thank you very much for your question. So if we keep using the coal and also natural gas, then it is necessary to use the CCS technology because otherwise it is impossible to achieve the net zero emission. But I know how feasible it is. Again, we need to carefully discuss because we also need to find the location of the CCS, and also not only the technologies but also the location of the CCS. We need to carefully discuss. So next point is that how to reuse the captured CO2. So that is another new discussion coming in the scenarios, but I didn't take into consideration that part into my scenario analysis so far. Okay, thank you very much for your point. Yes. Okay, so we would like to discuss more, but thank you very much for all questions. So let's move to the next presentation. So I would like to invite the next speaker, Dr. Sarita Sadhuhama Vishwanathan. She works as a postdoctoral fellow at the Social Assistant Division, National Institute for Environmental Studies in Japan. She has worked on national and international projects such as the CD Links, Engage, DDP, BICS, and also coal transitions. Her research focuses on the energy, water, environmental systems analysis, integrated assessment modeling, and social technology transitions, and institutions and policy analysis. Okay, floor is yours.
Thank you, Hanuka-san. I just wanted to ask if you could see the screen and if you are able to hear me.
Yes, perfect.
Okay. Thank you very much. Now I will start and I'll try to finish within the time limit that is provided. I will be presenting on the development and net zero transforming India's energy systems. I would like to acknowledge Professor Ambedkar, Rajiv, Deepthi, Vidhi, and Omkar, who are my co-authors in this research. So just to give a background, India is the second largest producer and consumer of coal. We employ almost 15 million people directly and in connected businesses. 4 states' revenue depend on coal royalties. 91% of our coal is thermal coal, which and 94% is basically obtained through surface mining. Even with so much coal that we are producing, we are still importing about 220 million tons of coal every year. We are the third largest consumer of electricity. However, our per capita consumption is one of the lowest in the world, with Canada and US having 12 times, 16 times the per capita consumption that we have. China has 5 times the consumption that we have. However, the coal mix is around the share of coal in our energy mix is around 56%, followed by oil at 25%. Coal is projected to remain one of the major sources for electricity generation. It basically constitutes 54% of our generation capacity and 72% of our generation share. Almost 39 gigawatts are under construction, and we have 20 gigawatts decommissioned in the last 5 years. At COP26 last year, Prime Minister Narendra Modi basically announced simultaneously installment of 500 gigawatts of solar target by 2030, which is 5 times the current capacity. We have electrified villages, but at the same time, stable access and affordability of electricity are still major issues in many parts of our country. Agriculture sector is one of the main sources for non-CO2 emissions, and 15% of our carbon emissions are removed by the LULUCF sector. Given this context, we have mapped almost 150 climate-related policies across India. And what we have observed is more than 60% of these policies were announced post-Paris. And we have dynamically improved or increased or updated our policies every year. A simple example being, we had 100 gigawatts of renewables before Paris, announced before Paris, which was increased to 175 gigawatts by 2022. And then in 2019, this was increased by 450. And at Glasgow last year, this was increased to 500 gigawatts. So India has constantly been raising its ambitions without even any external nudge from external players. What we have done here is, as Hanuka-san has presented the Aim and Use Global, we developed an Aim and Use India model, which we basically soft linked with other models. IMA-Claim is a hybrid CGE model times Markal to basically show the seasonal ranges. And also we looked into the BEX case study for India. We also soft linked the model with the CO2 fix and the Fable India model to look at the FLU sector for India. And this model has been developed for both energy and water resources to basically look at the water and energy supply as well as demand from various sectors. We did 3 scenarios, the current policy scenarios and 2 deep decarbonization scenarios, where DDS1 synchronized more with development, emphasizing on the development for India, and DDS2 emphasized more on the climate actions to move towards net zero. And as you can see from the graph on the right side, the DDS1 was able to remove almost 32 billion tons of carbon with LULUCF, while DDS2 was able to remove about 50 billion tons of cumulative carbon by 2050. And one can we also basically estimated in the future carbon budget, how much of the carbon budget would India consume. So for the CPS scenario, it's about 6 to 15%, and for DDS scenarios, it's about 4 to 12%. And one can see that it's power and transport sector that contributes the most when it comes to removal of carbon emissions. This is complemented by the forestry sector. Industry sector was observed to be one of the hard to abate sectors in the current net zero scenarios that we estimated. When one can see that sectoral decarbonization is significantly dependent on the decarbonized electricity, there are uncertainties at the supply level, depending on the type of fuel. How we develop in this decade would be a major source of how we move towards net zero. The future development of renewable energies, including the storage costs and the availability of critical minerals, the social acceptability and the geological uncertainty of CCS would play a major role for India. We did a very rough estimate of the coal that would be stranded in case we move towards the net zero. It is at a present value of almost 6.5 trillion USD. Renewable energy offers significant opportunities through modernization of grid and creation of jobs. However, one needs to very much be aware that this is a different skill set and at different geographical locations. So that needs to be taken into consideration when we are issuing the next set of policies. We did a very rough estimate of the power sector investments, and we found, depending on the scenarios, that we would need a total of almost 1.2 trillion USD for CPS scenarios. And as we move towards net zero scenarios, it could be around 3.3 if we are going for a 2070 net zero. However, if we ambitiously aim for a 2050, we may need more investments into the climate actions. Obviously, when we are doing policy implications, we need to look into challenges. One of the major challenges in the coal sector would be imports. There's a huge demand and supply gap. So how do we basically do the net zero import that the government had kind of announced earlier in 2016? With coal transitions and coal phase down, we will be aligned with a lot of stranded assets in terms of mines. In the transport sector for the rail fleet, the revenue would be less, and jobs in the mining sector. Similarly, in power, the cost of transitions in long-term lock-ins, the grid integration, flexibility, battery costs, and stranded assets would be a major challenge. And the industry would be hard to abate sectors. The large private industries are actively looking into moving towards net zero, having net zero in their industry systems. But it's the MSMEs that will require help from the government to transit towards the net zero scenarios. Even CCUS, there is uncertainty potential, but there would be a presentation by Professor Vikram Vishal, who would basically actually enlighten us on the CCUS in India. And obviously, production and storage and transport of green hydrogen is still uncertain, but there have been positive feedback from the industry who are interested in basically production, storage, and transport of green hydrogen. In transport, obviously, there's a huge push for electric vehicles. However, there is still charging infrastructure and battery costs that would be a major challenge, especially even in road freight. Forestry is a very aspirational goal. We need to maintain the forests. That would be kind of difficult in the next coming decades. Agriculture is hard to abate sector, and we have also found that it would be impacted by the climate change adaptation. So we need to look into these perspectives. Other challenges include vulnerability of the low-income and rural population, as well as the impact of global local financial crisis and future shocks need to be considered while doing policy, developing policies in this next phase. India will not attain net zero by 2050 under any scenarios that we have estimated. We need to involve the multi-transnational business and industry all over the world. International investments are required for India, especially to move towards net zero. And we require international support and facilitation for the vibrant carbon market. I am glad to inform that during the monsoon session, India may be basically looking towards starting a carbon market regulation, hopefully. Coal is a global concern, so there needs to be a global solution. International embargo on coal financing may create financial headwinds, so it could delay the process. Developed countries and India need to collaborate more towards incentivizing coal, which we are already doing through International Solar Alliance. We need to do the same for wind, BECCS, and green hydrogen fuel transformation. And we are talking about net zero, so we need to include all the 6 GHG gases, as well as bring adaptation and climate impacts into the discussion. This is just an example of the stakeholder engagement and outreach events we do once we are doing our estimations to get feedback from the stakeholders. So with this, I'll end. Thank you very much.
Okay, thank you very much for your presentation. So I would like to take the questions from the floor. Okay, yes, I saw your hand. Please. Dr. Pradhan.
Actually, I have only clarifications to seek. One is, in your net zero scenario 2070, have you used hydrogen technology or not? The second is, have you calculated the net jobs? Job loss, job gain, and minus the job loss. So these two clarifications.
Thank you very much, Dr. Pradhan. Yes, we have taken into consideration hydrogen in these scenarios, and no, the current model basically is directly looking at technology transitions. Indirectly, to a certain extent, through demand, we look at like work from home for transport and all that, but we are not looking into job loss. This is a limitation of the model. We have to do it outside model. So we have basically soft linked with a Geometry, which is an international model, which looks into job loss. And we have worked with them on this. So we have basically a paper under review for the same. But this model particularly does not directly look into job loss. We have to basically do it as like we give certain numbers, and there's a CG model which looks into the labor, hence the job loss.
Thank you.
Okay, thank you. Yes, I only take one more question. Okay, the first one, the Dr. Bhattacharya, yes.
Thank you, Sarita, for your presentation. So I have, a couple of questions, but depending on the time, I think you can choose to answer it. So first of all, I'd like to know that your model is running until 2050, I suppose, right? So, and because the India's net zero target is 2070. So why you have chosen 2050 first of all? Because, and you mentioned that by 2050 India has no option of becoming carbon neutral or the decarbonized. That is one. Second point is that in terms of your emissions, so how much are you seeing any kind of emissions peaking in your net zero? Because that is very important to know that during which time period the country is having a peaking. And finally, in terms of the demand side, so have you done any exercise on estimating the long-term demands? Because that you mentioned that the industry, transport, these are the main consumer of energy apart from. So the electrification of the demand is one option, and second is that how you can decarbonize those industry demands, and whether you have done any demand estimation in the long term, and how you have done that. So these are the three questions. Now it depends on you that you may choose to answer it.
Thank you very much, Dr. Bhattacharya. To answer your first question, you are completely right that we have presented it 2050, but I have now extended the model to 2070 because of our net zero emissions. And the very first scenarios, what we have found is it's very difficult to get net zero at 2070 for India, especially with the industry sector. The power sector would be easier to move towards net zero, but there are challenges. So that is the initial. However, we have not shown it in today's presentation, but we have done it. So that is your first. The second question, I forgot. It was related to. Could you repeat the second question?
Okay, time is limited. So
Yeah,
can
yeah,
you?
yeah.
Yes,
Then
can
maybe
you? Yeah.
Yeah, I'll just go to the third question about demand. So this I have used aim and use because we look at sectoral demands, and it is in great detail. So we basically exogenously have these demands for agriculture, industry. We have almost 20, more than 25 industries. We look into in transport also. We look at both passenger transport and freight, and then these there are huge numbers. So we have more than like 50 technologies in transport that we are looking at. For power, we are looking at more than 100 technologies in India. So various types of technologies have been captured from the demand perspective. And even building sector, we are looking both at the residential and commercial, and also looking at how smart grids could be. So we are looking both at the demand side, and then we have interlooped that how this demand side electricity is required by the power supply. So it's endogenous that the power technologies are selected. So from that aspect, it's kind of a complete model that we are looking at both demand as well as supply.
Okay, thank you very much for those discussions. So due to time limitation, I cannot take another question. So if you have, I saw your hand, one more hand, but please write in chat box and please communicate. Yes.
Thank you very much.
Okay, thank you very much for this presentation. So let's move on to the next speaker. So I would like to introduce the next speaker. So Dr. Avhinavi Trivedi is a consultant energy science technology with NITI IOG. Dr. Trivedi currently work area includes a hydrogen economy development. Yes.
Dr. Abhinav Trivedi is not present, so we can move
really?
to
Okay.
the next participant.
Okay, so we can move on to the next speaker. So I would like to invite the next speaker, Professor Chris Gray. Yes, Professor Chris Gray is a senior research scientist in the Linger Center for Energy and Environment at Princeton University. He is an entrepreneur and a former CEO and conceived the Rapid Switch Initiative, a major international interdisciplinary research effort that aims at identifying and resolving the critical bottlenecks that slow our progress towards deep decarbonization. So floor is yours. Can you share your screen?
Yes, I will. Can you hear me clearly?
Yes.
Okay. Right. Thank you, everybody. So today I'm going to take a slightly different angle, and it's looking at, my main concern is around the feasibility of these transition models. I'm going to introduce an idea called bridging capital discipline with energy scenarios in an effort to make them more feasible. So why am I concerned about the feasibility of models? These are extremely valuable tools, and they're really critical for helping shape the direction of policy. but they feature two interesting characteristics. One, the models are essentially simulating investors with near perfect foresight who have transparency across sectors and who respond rationally and instantaneously to price signals. And they also assume that new capital intensive mitigation assets like power plants, like BECCS plants, etc., are able to be conceived, designed and commissioned overnight. Whereas in the real world, we're basically talking about developers who are working under deep uncertainty. They tend to be risk averse and they won't allocate capital quickly. And so these projects also take years to develop. So a complex CCS project from concept through to commissioning could take 10 years. And it could be shelved along the way due to different challenges. And so this difference between how the real world developer and investor functions and how the models characterize them, I think poses a serious threat to how feasible these models are, unless we come up with some tools. And the key challenge is speed. In my view, net zero itself is not particularly challenging. Net zero, I would even say, is easy. The challenge is the time frame we've given ourselves. In the case of India, 2070, in the case of the US, 2050. And a lot of this speed challenge is driven by, path dependencies and chicken or egg problems, which are really quite critical to investment hesitancy. And I'm going to show you a piece of work we did for the US, which has helped us to, I guess, get a better handle on how to make our scenarios more feasible, which I think would be a useful thing for modelers and applied researchers in other countries to think about. So this idea is essentially reverse engineering the scenario. And we take the 2050 picture or the 2070 picture and we work back. You work back in time increments, maybe it's 10 years, maybe it's 5 years, and essentially map out what is going on in the scenario. So the first step is downscaling. And in the downscaling, we are essentially backcasting the mitigation of options, say renewables or say CCS, and we are basically working out where the physical assets will be at a very fine resolution. I would say the resolution needs to be socially and politically relevant. And you can take those results from any macro scale model, one of the IAMs that have already been presented this morning in that first talk. But now the question is, what does that look like on the ground? Once you've done the mapping, we then overlay the asset development and decision sequencing. So if you look in this sequence here, you'll see we've got these long duration construction, preceded by financing, preceded by permitting, feasibility studies, pre-feasibility studies. And so we have to understand the sequencing of these timings in order to understand how an investor is going to be behaved and when certain decisions and when certain policies have to be intervened. And that allows us then to look for what are the critical policy and investment interventions that governments or the private sector could do to try and accelerate through this sequence. And this is covered in a recent paper in Energy and Environmental Science. So if we talk about downscaling, I'll give you an example of how this works. We essentially start with our model. So this is showing the tons of CO2 in the United States being linearly portrayed down to zero, to net zero. And you can see, natural gas continues to play a role, as does gasoline. Coal essentially phases almost out completely and quite early, but there is some residual fossil fuel use used in 2050. And you can see that has to be offset by, almost 1.5, almost 2 billion tonnes a year of CO2 storage, which is through carbon capture and storage applied to a combination of natural gas systems, whether it be blue hydrogen or power, cement plants, and of course bioenergy plants to provide some negative emissions. So that's a useful thing. So now we need to think about what does that mean in terms of the capacity that needs to be built. And I'll give you an example here just of the power sector, but you do this same exercise for all the sectors. And so, you know, this scenario, when we unpack it, translates to these kind of installed capacities. So, you know, almost 4,000 gigawatts, 4 terawatts of power generation capacity, dominated by solar and wind, and that's unsurprising given their cost point today. But you can still see a role of natural gas here with CCS and some oil in the system, hydro, nuclear, etc. But wind and solar do the heavy lifting. And so you look at this and you say, well, there's more than 3 terawatts of wind, or at least 3 terawatts of wind and solar here. What does that look like on the ground? And so what we did is we mapped these assets using a set of bespoke algorithms that basically cost optimize the delivery of electricity to the demand centers, taking into account the lowest overall cost of generation and transmission. And we end up with this kind of map. So you see, you know, and we map these down to a 4-mile square radius, every renewable asset in the state, along with the transmission. You see the orange here are the solar, the blue are the wind. You can see lots of offshore wind. We build out a 3-fold increase in transmission, and of course the 3 terawatts of wind and solar. So that in itself is a valuable thing to do, and we do this for all sectors. We do it for CCS, we do it for the fossil generation that's still in the system, the cement plants, etc., the bioenergy plants, and so you have to do it for every system. And then you've got a picture of just how much deployment is going on where, taking into account the best quality resources, and these maps also take into account around 60 different exclusion criteria. They can be associated with social, environmental, cultural values, the locations of existing infrastructure, things like military bases, airports, etc. Okay, so that's a kind of a first step. That's given us one part of the picture. The next step is to then overlay the asset sequence. And so for this case, I'm going to take the example of CO2 storage. You'll recall there was about 2 billion tonnes a year, or 1.7 billion tonnes a year of CCS to be developed. And CCS is an interesting case study when it comes to how an investor thinks. And in my own career, I ran one of the world's first large-scale CCS projects, and they're very difficult to deploy. And in particular, they face a real chicken or egg challenge. And the chicken or egg challenge comes because we've got these 3 different projects going on. We need CO2 storage at scale. We need CO2 transport systems at scale, and we need CO2 capture projects, lots of them. If there's going to be 1 billion or 1.5 billion tonnes of CCS, we're talking about 1,000 or more, 2,000 individual capture projects that are going to be required, and that's a huge amount of storage. And the chicken or egg problem comes because before a capture project, be it a cement plant or a bioenergy plant, will embark on this lengthy decision sequence, which is, you know, up to a decade, they have to have confidence that will be somewhere to store the CO2. CO2 storage is the job of oil and gas type operators. And before they're going to invest a lot of money and time in this lengthy sequence to explore, appraise, and prove up CO2 storage, they're going to need confidence that there will be a large number of CO2 capture projects that will be viable and willing to pay for the storage. And before the pipeline investment is going to go ahead, they have to be confident there will be capture projects and storage projects. And so sequencing becomes a critical issue, and it's a critical issue mainly to actually overcome that chicken or egg problem. How do you synchronously expand the CO2 storage in the same rate as the CO2 capture and the CO2 transport? And, you know, I'm using the example of CCS here, but the same thing applies when you're comparing transmission with large-scale renewable deployment, when you're looking at green hydrogen, trying to stimulate the expansion of new green hydrogen demands with new green hydrogen supplies and the connecting infrastructure. And so we then overlaid this to see what we thought would work in terms of the policy and investment implications to develop CCS at that kind of more than 1 gigaton per year scale. And so if you look at the US today, we've got very limited CCS. These are the main basins in 2020. And so what we then do, having done our backcasting, done our mapping, and overlaid our sequence, this is what we recommended. So by 2030, we start to build out a pipeline network. Very few CO2 capture projects happening by 2030, but we've invested $100 billion exploring and appraising the CO2 storage, developing the beginnings of a national pipeline network. On the basis of that, we then crowd in CO2 projects. You can see bioenergy plants, cement plants, and natural gas plants beginning to crowd in because now they have confidence in pipelines and CO2 storage. And then by 2050, we were able to build out this large-scale, more than 1,500 CCS projects around the country, sited to this 4 square mile radius. And we've invested $300 billion in the sector and 100,000 kilometres of pipelines. So that's the end of my talk. It's really just to try and give you a sense of, I think we need to go beyond modelling and start to overlay some of the decision sequencing and the decision making and business processes that go with people trying to execute such an energy transition. And with that, I will take some questions if there is time.
Okay, thank you very much for your interesting presentation, another interesting presentation. So I would like to take some questions. Okay, I saw your hand. Okay, Dr. Pradhan.
Thank you. This is a really interesting presentation. Actually, I have two, simple-minded questions. One is, you are assuming the carbon dioxide reduction, a linear one, towards zero. So, why you are assuming, is it for, simplifying assumption or because it may not be optimal? That is the first one. And the second one is, in this risk reduction process, is there a role for the central bank?
So the first question, I think, we're assuming CO2 storage. We're not assuming CO2 storage. We actually have CO2 utilization as an option in the model. So we're starting with our macro scale model. It can choose to utilize CO2 or it can choose to store CO2. We did 5 scenarios. The scenario that I've just given you a glimpse of there was a scenario in which there were no supply side constraints. So renewables, CCS, everything was allowed to compete, including new nuclear. We also did a scenario where we did CO2 storage on the basis of environmental opposition. And in that case, we utilised the CO2 producing, chemical feedstocks and things like that. But certainly utilisation in our model is a lot more expensive, and that's why you choose storage. Now, the US also has really strong prospects for storage, and we've done quite a lot of characterisation work. If we were doing a similar exercise in India, I would have a very different view about CCS and storage in particular. And based on the background I have from industry, I think the prospects for large-scale CCS in India, particularly geologic storage, are going to be very limited, certainly in the mid-century horizon. And your second question is there a role for the central bank? Certainly, I think the speed and the scale of these net zero transitions will not happen without a high level of central coordination by governments. Obviously the private sector will mobilise most of the capital, But I think the central governments have a critical role in coordination and have a critical role in catalysing private sector investment with strategic investments, not just promoting demonstration projects, but actually looking for the strategic infrastructure that will catalyse private sector investment, like CO2 pipelines, like transmission, that sort of thing.
Thank you.
Does that answer your question?
Okay, thank you very much. Then I will take one more short question. I saw your hand, Dr. Bhattacharya. Do you have any short question?
I think Dr. Bhattacharya's hands has been up the whole time from the first.
Okay, thank you very much for your presentation. So due to the time limitation, let's move on to the next speaker. Then if you have any more questions, please write in chat box. Okay, I would like to invite next speaker. Next speaker is the Professor Vikram Vishal. Professor Vishal is an associate professor at the Department of the Earth Science, IIT, Bombay, and also the adjunct senior lecturer at the Department of the Civil Engineering, Monash University, Australia. I don't know how to read. He has won the Young Scientist 2017 award from the Indian National Science Academy. Vishal discovered a unique scientific method of the capturing carbon dioxide from the industrial units and thereby injecting it underground in order to avoid the air pollutants. So I would like to invite the Professor Vishal when you're ready.
Good afternoon, everyone. Am I audible to the online participants?
Yes, perfect. Thank you very much.
Thank you. So in the interest of time, some of the slides I may skip, but I think, Sarita laid the foundation for this. Dr. Sarita laid the foundation for the, talk that I'll be making. That's the role of carbon capture, utilization, and storage in net zero scenarios. So, so we host the National Center of Excellence in Carbon Capture and Utilization at IIT Bombay, which is funded by DST, and we have several of our industry and academic partners who are looking across the sectors of carbon capture, carbon utilization, sequestration, and cross-cutting systems. We all understand the energy demand is continuing to grow. India will be, using fossil fuels largely for the next few decades, and in that scenario, emission of carbon dioxide is inevitable. And we have tried to work out the scenario for business as usual. We are currently emitting somewhere around 2.8 gigatons of CO2 annually as a country, and the world is emitting somewhere around 36 gigatons of CO2 annually. And given at the business as usual scenario, we'll be emitting somewhere around 16 gigatons annually in India. Of course, that's not going to happen because we have announced for net zero and we have our commitments for reduction of carbon dioxide emissions. But the infrastructure growth, that is required will definitely bring further enhancement in, production of carbon dioxide and release it into the atmosphere. So in this regard, let us look at the CO2 cycle. We understand that in the fossil fuels and, for example, coal or shale gas or shales, the carbon is largely in a reduced form. But in a natural cycle, it is being oxidized to carbon dioxide, and then again through photosynthesis, it's being reduced back to carbon. So that's a natural biogeochemical cycle that's in the place in the earth. But what we are doing is essentially accelerating the production of carbon dioxide by the anthropogenic activities. The target is to continue with the work that we are doing, possibly also include the new technologies which are cleaner fossil fuels. But whatever CO2 is being emitted, we'd rather want to capture that and store it or utilize it. And that's exactly what is the content of my talk. So for this audience, it's pretty much evident what is CCS, or we capture the CO2 from two ways. One is from the point sources of emissions, which are the large point sources, or directly from the air using the direct air capture method. And once we have captured, we can convert it at the site to any useful product such as green chemicals, or we transport it and inject it into the subsurface as a CCS scenario. So in the utilization strategy, we understand there are different sets of chemicals that are currently commercially being made using carbon dioxide. And the products are big range, and then they have a market value. However, the scale that we are talking about is in gigatons. And can we really capture and convert the captured carbon dioxide into such scale of products? That is really, really challenging. The entire industry that runs this can get disrupted with the large scale capture and conversion to utilization of these products. And when we talk about billions of tons, which is thousands of millions of tons of CO2 being captured, currently the globe captures around 40 million tons of carbon dioxide, while we are emitting somewhere around 40 gigatons of carbon dioxide. So in that order of magnitude, we are offset, and we want to achieve net zero. That means no emissions after that. It will practically be impossible to just convert the captured carbon dioxide and still achieve net zero. In that scenario, carbon dioxide storage will become inevitable, and we must bust the myths around subsurface CO2 storage, because in the world, there are some 17 large-scale CCS facilities which are dedicated for subsurface storage. And for enhanced oil and gas recovery, for almost above 5 decades, we have been injecting carbon dioxide for enhancing the oil and gas production. So almost 300 plus million metric ton has been stored just for storage purposes in the world. And the theoretical capacity is in several tens of thousands of gigatons. So the question is, where is this capacity in India? I mean, that was the question in one of the talks that was being put here. So we have tried to look into the geological diversity in the country. We have almost all the kinds of reservoirs where CO2 can be stored, whether it is enhanced oil and gas recovery scenarios, or we have coal bed methane scenario where we can enhance CBM production by injecting carbon dioxide, or for pure sequestration, whether it is deep saline aquifers or the basalt formations. So the mechanism of storage is different. So in this book, we have compiled all the types of reservoirs where we can store carbon dioxide, and that's pretty much the target that we want to understand in India. So the question was, where is the potential for CO2 storage in India? And this is the map that we created in the first lockdown after COVID, because we found India's prominence by absence of this map in the world CCS map. So you can see that we have looked into potential for storage in the enhanced oil recovery scenario, enhanced CBM recovery, for offshore and onshore saline aquifers, and the basalt formations. So cumulatively, India has the potential to store around 395 to 614 gigatons of carbon dioxide. So this is a theoretical potential. When you look at the viable and the matched capacity, it will be less than that. So in that respect, even if our efficiency for this potential is 10% or 20%, we still can offset almost 40 to 80 gigatons, or rather up to 100 gigatons of carbon dioxide by going for geological sequestration. So we do not have to capture the entire 3 gigatons that we are emitting annually. Part of it can be captured, but the scale that we can mitigate is actually in hundreds of millions of tons. So this is published in International Journal of Greenhouse Gas Control. Now the question that came next are, where are these large point sources of CO2 emissions in the country, and how they are associated with the sink that we are looking at. So Professor Garg is here, and his group has done tremendous work on this mapping. What we have tried to do is bank on that and update on the geological map that we produced last year. And we looked into these cluster of these large point sources and related with the category 1 oil fields in India, which are currently producing oil. So the captured CO2 can be transported and used for enhanced oil recovery. And after that period, the entire storage space become available after EOR project goes over. We can store the injected carbon dioxide permanently into these reservoirs. And we have also produced this map on the right-hand side for India, which is linking the clusters that are of sources that are nearby. So you can have these common sources, whether it is cement or fertilizer or power plants, and then they can all be linked together as a common infrastructure and store in the nearby subsurface space, because subsurface potential of storage is huge. And that is why this kind of exercise will be useful, because the cost reduction can be happen because of the sharing of infrastructure. So this sort of a sourcing exercise, matching and CCS hub cluster is being done globally, and we are among the ones to produce that for the most recent updates for the Indian scenario. So the capture was indeed a challenge for the industries in India. So around 5 years ago, we were in touch with NTPC, one of the leading emitters of carbon dioxide. So we discussed with them how we can go and address the problem of capturing carbon dioxide. So partnering with Carbon Clean Solutions from the UK, we actually did the complete assessment of 600 tons per annum and 60,000 tons per annum of CO2 capture and conversion to green chemicals, that is methanol, soda ash, urea, and so on. And last year, it was very heartening to see that NTPC has actually announced the setting up of 20 ton per day CO2 capture facility in Vindhyachal, and they're converting this captured CO2 into methanol. So, sorry. the steps are, have been taken and responsibilities are being taken. I think these are all learning curves that we are getting, and we want to expand on this and really grow at the scale that we would be willing to. So it's very important to communicate. As we are academicians, we talk to the students and we often talk to the policymakers who also face the challenge. So several years ago, understanding about subsurface storage was really limited. So this is the model that we made here. What you can see, it's very interesting to see that in a reservoir rock. So normally in my class, I show this experiment live, but here I have this snapshot here. So when you inject carbon dioxide at the base of the reservoir, it rises up the plume here and it hits the cap rock, which is impervious rock, and then it forms a plume like this, and this is how it goes on to remain stored permanently in a geological reservoir. Now in a computer simulation model, I can do it in half an hour, but the idea was to develop a physical model and help the non-experts understand the subsurface CO2 storage. And therefore this is how the oil and gas has been there in place for several hundreds of thousands of years to, in some cases millions and billions years also, the oil and gas that was formed. So what we need is an efficient sealing mechanism for the injected carbon dioxide, and that's how around the world, wherever the CO2 has been injected, it has remained there largely as a safe place. Similarly, we developed a single fan direct air capture model for communication of science and technology of CCS to the general principles to the audience around. And not just us as faculty members, but also the students are fairly sensitized about CCUS. Last year, we participated in the $100 million grant challenge by announced by Elon Musk himself. And we won the prize, one of the teams to win the prize. We are the only team from India to win this prize, to set up a 1 ton per day CO2 capture plant at IIT Bombay, and we are converting the captured carbon dioxide to carbon monoxide. It becomes very reactive at carbon monoxide, and then from there we are making a series of chemicals such as salts. And subsequently, another team of students also won the minus CO2 challenge that talks about subsurface. So I see that the younger crowd in India is being fairly sensitized. They are getting the right set of training, and we can harness their training and knowledge to develop these kind of large scale projects in the country. So since this the conference is themed around policy, I must mention, so again 2016 and 2018, you can see the change in the number of people that attended. In the first, we had only a handful of people who attended in 2016. 2018, we had 175 footfall at the CCS conference at IIT Bombay. And subsequently, we are seeing that with the setup of national centers and now more policies around carbon dioxide abatement coming. So this was the roadmap that TIFAC prepared some 5-6 years ago, right? 2018. So we were one of the authors there. And I think that's the first document from any of the government bodies that has a clear picture on CCUS. But we have expanded on that with Ministry of Petroleum and Natural Gas, also including CO2 enhanced oil recovery as their policy. We released the draft CO2 roadmap for MOPNG last month. It is available for feedback. And we subsequently signed an MOU from IIT Bombay to them. And also, Niti Aayog is now developing the CCUS policy framework. Dr. Abhinav could not join, but he would have possibly mentioned about it. So, we are, I'm also helping the consultant to Niti Aayog for developing this framework. We are looking across sectors CCUS in India. And it is important for us to translate this knowledge that we are learning. So we are delivering continuing education program for the officers of different PSUs, which includes NTPC themselves. The second batch is currently learning. We are, the idea is to spread the knowledge and bust the myths around CCUS and allow the force to develop. And in that respect, ONGC has also mulled the strengths at IIT Bombay to upscale the CCS and CCS projects. So the road ahead for CCS in India is that there are tremendous efforts are required. The door is closing, and therefore CCUS will remain a key mitigation strategy for large-scale decarbonization. As per IEA estimates, it says that around 20% of global industrial CCS in India by 2060 could, in the world, can come from India. And CEW, mentions that the share of fossil energy can still be 19 to 30% of all, if we consider CCUS even in a net zero scenario. So that is the level that we are looking at. We need to accelerate our R&D and collaborate and bring the international know-how and all relevant policy support and funding for upscaling CCUS projects in India. And you can see this net zero scenario that I've taken from ETP. So I was one of the reviewers, and we were in Paris just before lockdown happened. And that's where we looked into different scenarios for net zero. You have different methods, whether it is electrification, clean energy, hydrogen, bioenergy, and so on. But even in that scenario, right from now until 2070, CCUS accounts for almost 15 to 32% of all the efforts that are required to, for the net zero transitions. So that's the kind of potential. And since globally, people are understanding the cost dynamics and all of this, so India has definitely time to, take leadership and, provide solutions not just for the country but for the world. But incentives such as Tax 45Q, you all may be aware of it. It is to incentivize CCUS projects in the US. $50 per ton and $35 per ton of CO2 mitigation either by pure sequestration or for utilization purposes. So India would need some similar incentives. We are working on that, and I clearly see that CCUS scenario will change rapidly than ever before. When we actually started working on it. With this, I'd like to end my talk. Thank you so much.
Okay, thank you very much for another interesting presentation. So due to time limitation, I would like to take only one short question. Yes, again, Dr. Pradham.
Thank you. This is very useful presentation. Actually, I just seek some clarification. One is how CCS technology is improving in comparison to solar and wind, and what is its how competitive it is in comparison to solar and wind as well. What is happening now and what is your forecast?
Yeah. Thank you, Professor Pradhan. Very relevant question, because we have to look at the host of technology solutions that are coming in place. I'll give you an example of direct air capture. 10 years ago, direct air capture, because direct air is capturing from 420 parts per million, very small amount of CO2 in the air. From that concentration, they're capturing and making it highly concentration, 99% pure CO2. From a flue gas, the flue gas CO2 concentration is 15, 30, or in some cases 70, 60%. Now, direct air capture 10 years ago was at $800 per ton. Now, currently, the people working on it claim it as $100 per ton. So accelerated R&D has changed the scenario for carbon capture. In India, particularly, globally, the cost of CCUS was somewhere around $70 to $80 per ton across different technologies, and the average number that I'm quoting. The NTPC plant, they're claiming at $34 per ton. That is happening right now. And I see that with accelerated R&D, developing more indigenous solutions customized to the sector that is required, we can definitely achieve it at $24 per ton. So this kind of cost reduction is happening because of the accelerated R&D. What we needed is the support from the industry to take forward whatever is being developed in the lab, and then to see, of course, along with the techno-economics. So compared to other technologies, the cost is being reduced. Solar, we all understand, was very expensive 25 years ago, but now it is as good as comparing to the power, cost of power from the fuel sector, from the coal. So this is how this scenario is changing, and I think further in next 2, 3, 4 years, it will become fairly, economical to do it. But some incentives are needed for the initial projects.
Thank you.
Thank you.
Okay, thank you very much, those presentation and also questions. Okay, let's move on to the next speaker.
Thank you.
Then I would like to invite the next speaker, and Dr. Johan Wettner is a research scholar associated with the Exploratory Modeling of Human Natural System Research Group in Advancing System Analysis Program, IIASA. Johan is currently involved in the establishment of the global phosphorus supply model, assessing geopolitical strategies to address short-term supply risk, as well as mid and long-term physical and economic scarcity issues. Okay, floor is yours. Can you share your screen?
Hi, everyone. Let me see if I can share my screen here. All right. Can you see my screen?
Yes, perfect.
Yes?
Thank you.
So my name is Johannes. I'm from IIASA. I'm actually doing this presentation on behalf of my colleague Nikolai, who is really the brain behind this study, but he couldn't make it. So I hope I can still give you some interesting insights. It's a bit less technical and more on the fundamental side compared to the other presentations that I've seen so far. So the social cost of carbon, I'm sure some of you have worked with it or at least heard of it. The idea is that you want to have a monetary value for the climate damages such that you can inform policies for CCS, policies for energy plants, and so on. This is why it's also relevant, I guess, for everyone here. And it's good to see how it is used. It is not explicitly a carbon tax because it's not policy prescriptive, but it can be used as a carbon tax, but it can also be used as a shadow price for government cost-benefit analysis, or even for private firms to see how investments should be done. It has been used mainly in the United States and in Canada to define fuel efficiency standards or for emission targets for power plants and so on. And Nordhaus once mentioned that regulations worth more than $1 trillion have been informed by the social cost of carbon. So it's an extremely political figure. And of course, there's a big debate about it. Some people claim that it's way too sensitive to some of the parameters which are inherently uncertain. So if you change the damage function in your model, your social cost of carbon might jump up or down by an order of magnitude, which has led the Trump administration to correct downwards the Obama administration's estimate. And others say, well, actually, we have climate targets enshrined in the Paris Agreement. We don't need cost-benefit analysis anymore to define an optimal temperature path, so to say. But there are also some prominent supporters of the concept, including Nicholas Stern, Joseph Stiglitz, and so on. I'm going through this quickly because of the time constraints. So if you take the DICE integrated assessment model and you look at the numbers, you realize that your social cost of carbon and your socially optimal marginal abatement cost curves in the model, they diverge. And it's generally accepted that your social cost of carbon is higher than your marginal abatement cost curves, than your marginal abatement costs, reflecting that your future climate damages might actually be higher than what a current market can support in terms of prices. But this figure has started bugging us. Basically, here in blue, you have the marginal abatement costs, and in orange, the social cost of carbon. And what this says is basically that your socially optimal price is lower than the level that you're actually abating. So what's wrong here? There must be something wrong. I'm going through this. So this is actually routed in the calculation method of the social cost of carbon. So the way this is done, you see how your optimal value, your social welfare in the model changes when you add a ton of carbon. So this does something to the model. You do the same for a unit consumption added to the model. So you add a ton of carbon, this does something to social welfare in total, you add a unit consumption. This changes your outcome, your social welfare somehow. And then if you take the ratio of these changes in social welfare, this gives you the social cost of carbon. But these perturbations of the model, of the calculation, they're purely exogenous. So you add a ton of carbon, which is not explained by any of the control variables in your assessment model, which means so your additional ton of carbon does not come from additional production in the model. It's just injected somehow out of control of policymakers. The same is with consumption. The additional consumption does not come from a change in the savings rate, it's just injected. And the conclusion is that the social cost of carbon is incapable of addressing changes in the control variable. So it's completely irrelevant as a policy tool to control your emissions. And this is actually a big issue, given that it's used for such big policies, right? And just to illustrate this, we did a bunch of very simple case studies. We used the social cost of carbon as a tax in the DICE model. So first we computed the social cost of carbon given a specific climate target. Then we re-injected the social cost of carbon as a tax to observe what kind of climate goal is then actually achieved. So the first one is the standard DICE. You can easily reproduce this. You just download your DICE model. You add a constraint for emissions, which have to be net zero or net negative from 2050 onwards. You get your social cost of carbon, which is the orange curve. and then you reinject it into the model and see what happens to abatement. So this is the socially optimal abatement path, which achieves net zero, so 100% abatement rate in 2050. Whereas if you use the social cost of carbon, net zero is achieved only by the end of the century, which also then leads to a much higher temperature in the end. So I'm going to skip the second use case. And the third use case is basically same story, but with a slightly adjusted utility function, which has also been published in high impact journals. And here it becomes devastating. So if you use the social cost of carbon to inform your policy, to control your emissions, you finally end up with you never achieve actually net zero emissions. So 60% abatement is the peak of your abatement strategy. And in the long run, you go to 8 degrees or something like this. Of course, this is the DICE model. It's all very stylized and simple, but it should illustrate that you should be very suspicious if someone gives you a social cost of carbon estimate to basically fund the projects that we've talked about in the previous presentations. That's it. Thank you.
Okay, thank you very much for another interesting presentation. So due to time limitation, I would like to take one quick question. Okay.
Can I ask?
Yes, yes.
Yeah, actually,
yes.
Due to time limit, the presentation was very short, so I didn't understand much of it. But what is your welfare function here? I mean, what sort of welfare function you are taking into account?
Basically, you're using the standard DICE welfare function, which is per capita consumption weighted by some elasticity parameters and discounted back to the present using a time preference rate. So this is a very standard DICE utility function, and you already have these results without changing anything about that. And the second scenario where this is just amplified, you remove the per capita weighting that you have in the standard DICE utility function.
I see. So,
yeah.
Okay. Thank you.
That's it.
Okay, thank you very much for those discussions and your presentation. So let's move on to the next speaker. We have 2 more presentations in this session. So I would like to introduce our next speaker. Please get ready. So Professor Basanta K. Pradham is a professor at the Institute of Economic Growth, University of Delhi. Dr. Pradham is a well-known expert on CGE modeling and analyzing issues related to climate change. Currently, Dr. Pradham is also working as an advisor, economy and employment for the Delhi Master Plan 2043. So, floor is yours.
Thank you very much for the opportunity. Let me share the screen.
Yes.
I don't know why the screen is not coming.
I think we saw your desktop monitor.
1 second.
Yes.
Yeah. Can you see the screen?
Yes, but can you make it to the slide presentation mode?
Okay. Is it okay?
Yes, perfect.
Yeah, thank you very much. I have my 2 co-authors, Dr. Sangeeta Yadav and Dr. Jaideep Ghosh. They are also here. So let me start the presentation because time is less, and I'll I have a lot of slides, but I'll focus only on the some results. So I'll though I have many beautiful slides, I'll just skip them. I'll straight go to because these are the background, and there are many interesting presentations before me, and all of you know this background, so I won't go through this. Basically, I just want to say Indian cabinet recently, committed, approved this one is to reduce to 45 45%. The other is to reach net zero. No, the other is to to have 50% renewable energy in the energy mix. So let me go to yeah. So my study is basically, it's not a physical study, physical model. This is an economic model, and I'm using a general equilibrium model, computable general equilibrium model, and this is work in progress. We have done simulations till 2030. We are working, to do it till 2070. So we are trying to include technological progress basically in hydrogen and CCS. Then we'll take it to 2070. But I'll present my results, whatever we have found till 2030. And as many of you may be knowing, CG model is a equilibrium model. It takes both demand and supply sides, and demand and supply, they come from optimizing process of producers and consumers. And there is a government which intervenes in policy in this model. And we have this is a standalone model. So we talk only about India, and though there is an external sector. In this model, we have many standard features, and I don't want to go through in detail in this. Only thing we have used for consumers, linear expenditure system. Then we have taken these things into account in your model. Basically, 500 gigawatt renewable energy by 2030. And we have taken into account in this model many policies which are already existing in India, like PAT, ECBC, Ujjwala, and many others which I have not put here. And our model results, if you look at GDP impact, then GDP impact, we have two growth scenarios. One is we call low growth scenario, the other is called high growth scenario. And in high growth scenario, how much GDP is growing in comparison to, we have a business as usual scenario, and we are comparing it with simulations. And then we show like what is the relative difference between BAU and simulations, both in high growth scenario and low growth scenario. So if you look, there is slight, if in high growth scenario and also in low growth scenario, there is slight, in fact, gain in GDP. So this is not a usual result, though, there are some, papers in the literature we have seen that, including one of our own earlier paper in energy economics. Then if you look at emissions, if you look at low growth scenario and high growth scenario, and in simulations, you will find they are almost equal. That means why this is happening, because in the low growth scenario, your the energy intensity in the GDP is higher. So that's why the total amount emitted in this model is almost equal in the low growth scenario and high growth scenario of GDP. Then if you look at emission intensity, in the high growth scenario, it is coming, from 18%, it is coming down to 14%. In the low growth scenario, it is stopping at 15%. So you are a little higher gain in the high growth scenario. This is the same thing getting repeated. If you look at share of electricity in this for various sources, then you will find that in the low growth scenario, there coal still dominates, but in the high growth scenario, by 2030, solar and wind, they will dominate. They will be higher than coal, basically. So what are the major conclusions? Major government initiatives which are in already in effect, they play a significant role in this. High probability of meeting NDC targets under high growth scenario. There are two regions. High growth scenario means you need investment. So high growth scenario, you will have more investment, and the other is basically to dismantling coal is more it's not an easy process. Then target achievement depend on all these factors, as we know, and here in the model also, economic, technological, as well as financial factors. External factors are very important, and we argue that unless there is substantial transfer, we have to generate more finance internally, but unless there is substantial transfer of finance as well as technology, it will be really difficult to achieve net zero, even to meeting these NDC targets by 2030 also. Then we have another paper where we have this conclusions which are useful, is basically with respect to just transition, because here we find income distribution will be more affected if you go on increasing carbon tax. Carbon tax is a good way to control, but it affects income distribution very badly. That's what we find. So if you achieve it through technological progress, then income distribution also becomes progressive. So that is the main finding, and I'll stop here. Thank you very much.
Okay, thank you very much to sharpen your presentation. I would like to take short question, if there are any. Okay, how about the question from the venue? Okay, thank you very much. Thank you for your another interesting presentation. So I would like to let's move on to the next speaker. Yes, this next speaker is the last presentation. I would like to introduce Ms. Anjana Das is the Senior Energy Consultant at Integrated Research and Action for Development. She is currently working on the development of the climate neutral socio-economic development strategies for India. She is also developing the India power system model using message software, which will be extended to the whole GHG system for analyzing net zero strategies for India. So, floor is yours.
Thank you, Mr. Chairman. So my presentation is on pathways to net zero emissions for the Indian power sector, technology options and cost. You all know India has India has made a pledge of achieving net zero emissions by 2070. So how to arrive there and what would be the cost implications? These are some of the questions need to be answered. So we started with the power sector because power sector is the largest contributor of GHG as well as CO2 emissions. It contributes about 50% of the total CO2 emissions of the country. And growth potential is very high in power sector. Secondly, mitigation technologies of power sectors are mostly available. And thirdly, third reason is once it is decarbonized, once electricity is green electrification can be used as one of the economic tool to decarbonize the rest of the economy of the country. So that's why we started with the power sector. So objective of the project was assessing technology and cost implication of why it is there, this one, of achieving net zero of the Indian power sector by 2 target years, 2050 and 2060. So we tested 2 years, 2050 and 2060, because cost can be different in different years. And also we tested 2 years, 2050, 2060, previous to 2070, because as I said, once electricity is green, once electricity is decarbonized, green electricity can be used to decarbonize the rest of the economy. So that's why we have considered 10 years ahead, up to 2060. Research, the focus was on role of different technologies, like how the technologies will be, technology, what kind of technologies will be needed to decarbonize the Indian power system. It's a detailed list of technologies: solar, wind onshore, wind offshore, battery storage, then coal power plant with CCS, and palm storage, and so on. Cost of emerging technologies are declining over the years. Last 10 years, we have seen cost of solar PV, capex of solar PV has declined by almost 85%. So what would be the implication of different cost reduction rates of emerging technologies in decarbonizing the power system? And then the potential of various renewable resources are still not known in India, or some of them are old. So what would be the potential requirement of different resources which will play dominant role in decarbonizing the system? In the present dominance of intermittent technologies like solar PV, wind, and so on, what would be the role of dispatchable technologies like coal power plant with CCS and nuclear? There will be, as I said, there will be a dominant presence of intermittent technology. So what would be the implication on storage? Cost of reaching net zero by different dates in terms of investment and energy system cost, what would be the climate finance implication, and some of the policy implications. So we used a message model of International Atomic Energy Agency. This is a technology-rich model. And this is a dynamic least cost linear optimization software. Time frame of the analysis is 2015 till 2085. In case we need to see the year, 2070 and so on, with 5 years period. Annual electricity demand is exogenous to the model. Given the dominant role of dominant issues like intermittency and flexibility, model captures the seasonal and daily variations of load as well as energy supply from different sources for 280 time slices, meaning it balances the energy demand and supply for 280 time slices, which comes from 12 seasons. Each month is representing one season, and average daily variation of a day is representing, a typical day is representing a month or season. It's a technology is the dominant solution, right? So we have considered detailed list of technologies, all possible list of technologies like pump storage, hydro, power plant with CCS, battery storage. So these are some of the little bit unconventional technologies which are modeled. So key assumptions include all cost at 2015 USD, real discount rate 4%. This is a process model or technology model. So technologies are represented with technical and economic parameters. First decline in capital cost of RE as well as storage technologies are assumed. And then we have assumed CO2 storage potential of 25 gigaton. I think one of the Vishal paper we have also seen, which it talks about 45 to, I think, something like 100 gigatons, and we have taken 25 gigaton for the power sector. And CO2, there is a large variation in CO2 transportation and storage cost. Like if I remember correctly, Northern Light project of Norway, it's reporting something like 50-60 euro per ton of carbon CO2. So we took this assumption, I think, from a paper of MIT. And I have, so this is a $15 per ton CO2 transport and storage cost, because I have seen if it is something like $30, it is not picked up by the model. So this is a least cost model. So model will always go for least cost option, which may be unrealistic. So to prevent that, we have imposed some upper bound of these technologies like nuclear, solar PV, wind offshore, and so on. These upper bounds sometimes are from government report, like we know pump storage potential is about 96 gigawatt, large hydro potential is about 145 gigawatt, and some of the potential are not known. So these are based on a expert judgment or published figure. So as I said, electricity demand is exogenous to the model. So demand is has been estimated based on GDP growth and GDP electricity elasticity. So this right side graph shows you the demand projection. Blue line shows the annual demand growth. So you can see huge growth in annual electricity demand, which is quite expected because current per capita electricity demand of India is very low. So by 2050, electricity demand will be about 7,000 terawatt hour, which goes up to about, I think, 9,000 terawatt hour in 2060. So despite this growth, if you see the black figure, this is actually electricity consumption per capita. So by 2050, electricity consumption per capita of India will be about 4,200 kilowatt hour, which is even 20% lower than what is China's per capita consumption today, which is about 5,300 kilowatt hour. And by 2060, per capita consumption will be about 5,600 kilowatt hour. So we developed 3 scenarios with the model. Model has been used to simulate 3 scenarios. Business as usual scenario includes all policies that are in place, in like 175 gigawatt of renewable capacity by 2022. Then this new pledge, which is made in last COP26, 500 gigawatt of non-fossil sources, which includes renewables, large hydro, nuclear, by 2030. So those have been included in the business as usual scenario. And in BAU scenario, there is no constraint on emissions. Then we have developed 2 net zero scenarios, NZ50 and NZ60. So NZ50, their emissions are constant. So power sector CO2, we have assumed power sector CO2 emissions will decline gradually. And by 2050, it will stabilize at 200 million tons or 0.2 gigatons. Why this? Because India has a large sink, so we have assumed some amount of positive emissions will be allowed by the power sector. So from 2050, it will continue with about 200 million tons. NZ60 is same as NZ50, but here instead of 2050, power sector emissions decline up to 2060 to reach 200 million tons, and then it continues thereafter. So this is the emission trajectory. So black line shows the emissions from the this is the model calculation. This is the emissions for the business as usual scenario, which is the unconstrained emissions, and you can see it is growing and growing. Although growth has been slowed down after some time. So blue line is the emission trajectory, which we have calculated and imposed to the model as a constant. So in this case, emissions will peak in 2030, and then it will gradually decline to 200 million tons in 2050 and will continue thereafter. And orange line shows the emission trajectory for the NZ60 scenario. Here emissions peaked in 2035 and then declines thereafter and to reach 200 million tons by 2060 and continue thereafter. In the next couple of slides, I'll show you some of the results. So I start with what would be the power generation and storage capacity requirement for the decarbonized power system. So I am not showing any BAU scenario results because BAU scenario will be all dominated by coal and coal and coal. So these are the capacity projections for net zero, two net zero scenarios. So left side shows the NZ50 capacity growth and requirement in NZ50. So this includes fossil, non-fossil. Non-fossil includes nuclear, large hydro, and all renewables, and then storage capacity. So you can see total capacity requirement is huge. Today, India's capacity is about something like 400 gigawatt. So by 2030, it will be about, to meet the demand, it will be about close to 900 gigawatt. And then thereafter, it will only increase very rapidly because why? Because you can see it is dominated by non-fossil sources and largely solar PV and wind. And these two sources are having low availability factors like 20%, 25%. So they need large amount of capacity. So you can see by 2040, capacity will be, generation capacity will reach about 2000 gigawatt. And that will further increase to 3,200 gigawatt in 2050 and about 4,700 gigawatt in 2060. So, and this will be supported with huge amount of storage capacity, like 694 gigawatt of storage in 2040, which increases to about 2,200 gigawatt of storage in 2060. And this storage includes pump storage and battery storage. Similar result we see for NZ60 as well. So this slide, in this slide,
can you conclude around 1 minute?
1 minute?
Yes, the time is, yeah.
Okay.
Shortly, yes, yeah.
Give me 2 minutes. Yeah.
Yes,
So
yes,
this slide shows the further technology breakup. One main message is conventional coal will peak in 2030 in case of NZ50, and it will decline thereafter. This is an important message because coal is the largest consumer of power sector is the largest consumer of coal industry and employs 14 million people. So that can be somehow that problem can be addressed with the deployment of coal plus CCS technology, which enters in the system from 2035, and by 2040 it reaches about 218 million tons. In the NZ60 scenario, we get the similar results, but here conventional coal, the peaks in 2040 instead of 2030, and penetration of coal plus CCS is slightly lower than 2050 case. So this slide shows, this graph shows further the renewable plus storage. So you can see all yellow and blue, these are wind and solar PV capacity. So they will dominate the power system, and by 2050, about I think 80 to 85% of the capacity will be solar PV and wind, and that will go further up by about 90%, which will be solar PV and wind in the decarbonized power system. And there will be huge requirement of requirement of storage. And given the battery storage cost is declining rapidly, so it will be mostly battery storage and 6 hours battery storage, because mostly dominated by solar, so which provides energy only 5 to 6 hours a day. So you need longer hour battery storage. So this is the generation pathways. You can see we need huge amount of generation to meet the growing demand. So by 2050, demand generation will be about 8,000 terawatt hour, which goes further up to 10,000 terawatt hour by 2060, and about 85 to 90% of this generation will be solar PV and the wind. in as against today, it's about 75% comes from coal. So the system will be very different the 25, 30 years from now. And NZ60 scenario also shows similar pathways, generation pathways for the power system. So this is the merit order dispatch. So how power system will be 30 years from now is very different, and operation also will be different. So I quickly give you this. Yellow color is the generation from solar. So which is between 6 to I think 4 o'clock in the evening. So red color is the demand. So during sunshine hour, battery needs to be charged. So negative axis, this orange color line is the battery storage, and battery discharge during after sunshine and before sunrise, which is showed in a purple color. So now I show some cost implication. So cost implication is huge, so which is expected. So additional investment requirement to achieve NZ50, that means decarbonizing power system by 2050, which will be about 2.5 trillion USD over the BAU. And so it shows that the requirement, what kind of climate finance will be needed. And energy system cost is also higher by $2.3 trillion. That shows the implication on energy supply price. NZ60 scenario also equally expensive, but little lesser than the one which if we achieve the decarbonization by 2050. So I quickly conclude. So dominant technologies for decarbonizing Indian power system include solar, wind onshore, offshore, nuclear, coal power plant with CCS, large hydro, battery storage, pump storage, very different set of technologies which you see today. Then 2000 gigawatt of solar PV and 1350 gigawatt of wind capacity will be needed by 2050, which is huge and which is a huge amount. And so there is a strong need for assessing these potentials of these technologies, whether these kind of potentials are existing in India. Then 2.5 trillion additional USD, the additional investment will be needed. That clearly shows the need for climate financing. So on some of the key the policy recommendations are achieving net zero Indian power sector is challenging and needs progress in technical and economic performance of technologies happens as assumed in our study. International assistance on technologies are needed. Long-term, it needs long-term low-cost climate finance. Then domestic policy standards and regulations are in place. An important thing, issues on minerals, because battery storage, batteries needs different kind of minerals, same solar PV and other technology. Skills, R&D, local manufacturing are need to be addressed. And then well-coordinated engagement of all stakeholders, government, industries, and public are needed. That's all about my presentation. Thank you.
Okay, thank you very much for another interesting presentation. But time is running out, so I'm sorry that I cannot take questions. So if you have any questions to her, please directly ask her. Okay, thank you very much. Okay, we finished. So thank you very much for all presenters. I hope you enjoyed all presentations and discussions. I would like you to applaud our speakers. And I'm sorry that we are way a little behind the schedule before the panel discussion. So we will close session 9 now.
Thank you very much, sir. As we have reached to the end of the session, we would like to thank each one of you for gracing us with your presence. On behalf of TIFAC and IIASA, we would like to felicitate you for being our honorable speaker of the day. So, may I request Vikram Vishal sir to felicitate ma'am. Now I would request ma'am to felicitate sir. Okay. Okay.
Thank you very much. Thank you for your presence.
Very much.
Okay, thank you very much. See you.
See you.
Bye-bye.
Thank you. Thank you.
ठीक है तब मैं हेलो या डॉक्टर भट्टाचार्य Dr. Johannes and Jaydeep, we have actually concluded the session here.
Okay, I think, yeah, we'll be joining the other session.
Yeah, please join in the hall 1 link.
Yes.
So we are starting plenary there. Thank you.
Thank you.
Dr. Johannes and Dr. Jaydeep, are you listening? We're going to close this session. Please join in the hall 1.
I'll give you इसी language.
मैं मीटिंग को क्लोज कर रहा हूँ.
Hey, language.
I'm saying end meeting कर रहा हूँ.